Okay. So, hi everyone, and thanks for joining us to this 2026 edition of the Dafny workshop. I'm Yannick Moy, and this is Stefan Zetsche, and we're organizing this, and we're very proud to have you here. So that's the third edition after our first edition in 2024 and the second last year. There are many good things that carried over from the last year. So in particular, a very rich program, as you'll see. We had 28 submissions to the workshop, out of which 17 were selected. So that means there's a tight schedule with 18-minute talks. So 4 speakers. When I'll show you my hand, that means you have 5 minutes total. And when I show 3, that means that it's time for a switch of slides. So the new speaker is invited to come and change the slides while we're doing the Q&A. In case the first speaker wants to have Q&A, otherwise you can continue talking. But yeah, at the end of the 18 minutes, we really need to change speakers. So in total, yeah, we had 17 papers accepted, 11 rejected. So thanks to all who submitted. That was a kind of tough bar because we had to accept only papers with 2 accepting reviews. And thanks to the 8 reviewers from the program committee and the steering committee, some of whom are here today. We had good things from last year that we repeat this year. So of course, you'll have news from the lab and news from the field on what's new in Dafny and what works in Dafny. So that will be the topic of the third session this afternoon on applications and lesson learned. Like last year, we also finish with a session on LLM, autoactive verification, whether it's to synthesize correct by construction codes or to enhance verification automation. And what's new is that this year we've expanded the scope of the workshop. So it's not only about Dafny, it's about all autoactive verification platforms. So in the second session on development of autoactive verifiers, you'll have talks about Caesar, Y3, Spark, Varus, Velvet, Veil. And in the first session, right after my introduction, we'll also have Dafny, of course, and F-star. So talking about F-star, I'm very pleased to introduce Karthikeyan Bhargavan, our invited speaker today. Karthik is currently Chief Research Scientist at Crispin, a company he co-founded to develop and commercialize high-assurance crypto software backed by formal proofs. And that's why I'm interested here. That's exactly the kind of developments we'd like to see from the community. And I'm speaking here on behalf of both industry and regulatory bodies. Before that, Karthik was leading the Prosecco team at INRIA in academic research, which developed a number of tools and proven implementations of crypto primitives, crypto protocols, and as part in particular of the Everest project. And you can see all of that in their recent top last paper, giving a retrospective and perspectives on the Everest project. And I think it's a must-read for everyone in this room. So with that, I'll leave it to Karthik to dazzle you.
Thank you. Sunday morning. It'll be very liberal with people coming in. Well, I'm just introducing myself, so it's kind of okay, I think, yeah. So we all have a background, and a lot of us have a background in programming languages and formal verification, but we find ourselves spending a lot of time applying them to cryptographic systems and talking to cryptographers and practitioners. So usually I'm giving these talks in front of cryptographers, practitioners, telling them, hey, you guys should use formal verification, look what we can do. And today I'm going to reverse that. I'm going to tell you guys what we've learned by applying these tools to crypto. And maybe this might point the way towards some interesting research ideas, I don't know, but at least you'll learn what we learned. All right, so when I talk about real-world crypto, basically what I'm saying is the things that we use on a daily basis. So this is my bank website, LCL, and the only reason I am trusted enough to kind of do my banking on it is that if I click on the lock, it tells me what actually it's doing. And what it's doing is it's running a protocol called HTTPS, inside which there is a cryptographic protocol called TLS, which uses some classic crypto constructions implemented by some standardized kind of cryptographic algorithms that are well considered. And in one form or the other, this TLS protocol has been around for 30 years. So it's been highly studied, implemented many times, tested to death with lots of fuzzers and everything. So it's like a critical component of the web, very well studied. So in a way, by now, after 30 years, we should really know how to do it well, how to do it properly. But of course, when we started looking at the protocol, that wasn't the case. So in the 5 years we studied the protocol, there were dozens of attacks, each of which had an acronym, a website, a logo, press releases, and so on. So it was looking like a pretty bad situation. And it wasn't clear why this kind of protocol is so hard to get right in a world where we already knew by this time to verify operating systems and compilers. And if you go deeper into all of those attacks and try to classify them, you'll find that there are kind of three kinds of issues that come up again and again. The first is, well, over 20 years, any system like TLS is going to use a lot of cryptographic algorithms, a lot of options. And some of them are not going to stand the test of time. They're going to be weak by now, right? They were strong in 1994, but they're weak now. And in protocols that have been widely deployed, it's quite hard to remove features. You can add features, but removing features is quite hard because of backwards compatibility. The second category is protocol design flaws. And this is very rare, but when it happens, it's pretty devastating because it means that you have to change the protocol, to go through the standardization body, make new implementations, propagate them everywhere, and so on. So those ones do happen, and some of them are, and some of them, and they can be pretty bad. But the most common issue, of course, like nobody in this room will be surprised, is implementation bugs. Tons and tons of implementation bugs because there are tons and tons of implementations with varying quality. What's interesting also is that a lot of the bugs that I showed you in the previous slide, which kind of deserved an acronym, were a combination of these. So they use a combination of these things in ways that all the tests and fuzzing and everything else that people were doing on TLS could not catch them. It required quite a lot of ingenuity and therefore papers and acronyms to actually find those attacks. But this, because testing fails in the situation, is also where we think is a perfect example for why you can apply formal verification. So there is this whole field that has now come up, which some people call computer-aided cryptography, some people call this high-assurance cryptography, which basically is what you would think. It's basically taking formal verification tools to produce machine-checked proofs for cryptographic designs, cryptographic standards, and implementations. And the key point here is that crypto, like many other systems that we know and rely on, continuously evolves. People keep standardizing new things, implementing new things, optimizing things, trying to do things in new ways, and so on. And so whatever you put in place has to basically stand the test of time. You have to be able to maintain it, keep evolving it as the systems evolve. And there again, I think formal verification, especially of the kind that we all do, has an advantage there. Because once you have done all the work of building a formal proof, hopefully rerunning it as the system evolves is much cheaper than doing a pen and paper or manual proof again and again, right? At least that's the spiel. A lot of the work I'm going to describe today is going to be taking examples from the last 10 years of work, the first 5 years of which was more like in the research phase, the Project Everest, like Yannick was mentioning. And yeah, you can go read the paper about that. And in the last few years, I've been working at this company trying to take the ideas that we learned from Project Everest and apply them to new industrial projects, often taking lessons that what didn't work and trying to do it in a better way. So you'll hear of my experiences in both of these. So let's take the first example about crypto. When you say crypto, you typically start at the bottom with cryptographic algorithms, cryptographic libraries. And what are these things? Well, you all are using them. You may not know it. Every single operating system has its own crypto library. Every single web browser has its own crypto library. Most languages now have embedded crypto libraries. Even IoT devices, however tiny they might be, have tiny little crypto libraries running inside them. Okay, and there are a whole bunch of these, right? And they basically form the trusted computing base for the entire cybersecurity ecosystem. Well, that's part of the trusted computing base. And if you go hunting for the vulnerability reports, this is just 2025. I think there were 12 in Wolf SSL, 6 in OpenSSL, and some of the other ones have similar numbers. Some of them don't publish vulnerability reports, so you don't know, but there's a significant number of vulnerabilities in each of these. And they are the kinds of things you would imagine, memory safety bugs, also interesting ones like side channel bugs, and some functional correctness bugs. And when we started this whole project, there was no verified crypto available for people, none of it. Today, the situation is much better. There's a dozen verified crypto libraries which are now available. And this is basically the effort of the last 10 years. Okay? And using a wide variety of techniques. And I'll talk about some of them, but there's many, many. And even this year, we expect at least 1 or 2 prominent companies to announce verified crypto libraries. So verified crypto has now become like a thing. Everybody does this. Okay? So the good news also is that for any crypto algorithm that you might want to use today, you shouldn't want to use like ancient stuff. Any crypto algorithm that has been standardized you want to use today, there is most likely a verified crypto implementation of it. Probably it's open source in a very liberal license. And it's very fast. You don't have to sacrifice performance. Sometimes, usually, the verified implementations are even faster than the unverified implementations. It's a bit unintuitive, but we'll talk about why. And all the proofs are mechanized. You can read on them yourself, and they've already been deployed. So if you go to AWS, you use Firefox, you use Chrome, they're already using verified crypto. So that part of it, success. You can almost declare victory there. So let's see what these guys are doing, what we've been doing all these years to make this kind of thing work. At a high level, the verification workflow is nothing. It's almost exactly what you would imagine. We start from a standard. So all of the crypto things that we're talking about are usually standardized, either by the NIST or the IETF. And the standard is a mixture of English and pseudocode, and pseudocode is written in some Python-like language. And then it has a bunch of test vectors. So that's kind of what a standard looks like. Usually it's much bigger than this, but whatever, right? So of course, the first thing you have to do is to write a formal spec for this. And since cryptographic algorithms are really just mathematical functions, often can be written very succinctly, you can write them in any language of your choice, and I don't even have to tell you how. This is what it looks like in F-star, this is what it looks like in EasyCrypt. Some look more imperative, some look more functional, but on the high level, this is just bit string to bit string functions. Okay? Anybody can write this in any, you can write it in Lean, Rock, people do all of this stuff. So once you have the formal spec, you're going to write the implementation, right? And this is where, of course, the intelligence comes in, because the implementation often has to be optimized, both for runtime and for memory, depending on what kind of place you're deploying it in. And so people do lots and lots of tricks. Okay? In fact, cryptographic algorithms sometimes are the performance bottlenecks in several settings. For example, for web servers, there can be a performance bottleneck. In IoT devices, crypto, in the size of the crypto itself, can be a bottleneck for the IoT device. So it's not just, oh, let's optimize this one cool thing. It's actually the central thing that we have to optimize. So people end up writing very optimized implementations for these. So in F-star, for example, you write something like that, and it gets compiled into C code. So it looks something like that. So whatever. Or if you want to really, really optimize it and have a lot of control on the low-level implementation, you might write it in a pseudo-assembly language. You can write it in Jasmine or a language called Whale, which we'll talk about later, perhaps. And in this case, you're really writing it like assembly code in a way that can be compiled down to, for example, in this case, this is AVX2 assembly for Intel. So it's really focused on performance, but also on low-level control of what's actually going to happen at runtime. OK, so you've written your optimized implementation. You have your spec. So of course, the question is, how do you verify it? Most of the people in this room should be able to verify these kinds of algorithms. It's not shocking. It's an input-output mathematical function. Implementation show that they have the same behavior, right? So typically, you prove memory safety first, and you prove functional correctness with respect to the spec. There's a little bit of interesting things going on in terms of proving that your code is not exposed to certain categories of side channels. And there, maybe it's a bit different from what we do in normal software verification. But again, we convert it into a verification problem. So let me give you an example on why this is interesting, where the challenges come from, and so on. So a central, before the post-quantum transition became such a big thing, everybody was using elliptic curve cryptography, which centrally uses a construction called Diffie-Hellman. And if you think of Diffie-Hellman in the school book sense, it's basically something like this. You're doing exponentiation modulo some prime. Okay? And so the central computation there is modular multiplication. A times B modulo some prime P. This is field arithmetic. Okay? So prime field arithmetic, implementing using modular multiplication. Often this one operation, modular multiplication, can be the complete performance bottleneck for a server or for an IoT device. Okay? This one operation. So this really requires a lot of attention, and therefore people optimize the hell out of this. And why? Well, let's go back to school. How does multiplication work? Well, if you do bitwise multiplication, it's basically something like this, right? This is classic textbook multiplication. And if you're doing it with 256 bits instead of 4-bit numbers, it basically is something like this. You divide it up into 64-bit components because that's the word size on your machine most likely. You multiply it, and you get 128-bit values for each of these ones, and you do some carryover, and you carry over. You do all the additions and so on until you get the full value. And when you get the full value, you have to do the modulo p. And so you do reduction steps. It brings you back into a much smaller result. Okay? So, and you basically, every multiplication is something like this: multiply, carry, add, reduce. And if you always did all the reduces, and if you always did all the carries, because there is a chain of things which cannot be parallelized, this thing ends up being quite slow. So all the tricks for optimizing this are in trying to parallelize as much as you can the additions, the carries, and the delaying the reduction as late as you can. Like if maybe I can do 5 additions and the thing won't overflow, and then I can reduce it rather than reducing it every time. And each of those optimizations can gain you like 3%, 5%, 10% performance improvement, which translates to millions of dollars for AWS and Google and so on. But then, of course, when you're trying to optimize this, you end up with bugs. So these are all bugs that people have found in exactly these kinds of implementations, modular multiplication, et cetera. So most common one, actually, what happens is integer overflow. So there was some carry you were supposed to do somewhere, and you forgot to do that carry. And now, when you do an addition by 1 or whatever, the thing is going to overflow the 64-bit value. So if you overflow it, on some languages, this is a runtime error. This undefined behavior runtime error, it might crash. But almost all situations, it's not going to crash. It's just going to roll over. It's just going to wrap around. So you're going to get a wrong result. Okay? But the wrong result is going to happen with very low probability. Right? It's only going to happen when you are really overflowing that particular integer. So a lot of tests could pass. And there might be one test every once in a while that might fail. And if you rerun them in a randomized way, again, it might pass. So testing was very unlikely to find these kinds of little carry failures, which are only going to happen with low probability. Of course, there's also arrays here, so there's buffer overflow, underflow, and there could be side channel attacks. These are all low probability attacks, which testing doesn't usually find. So what is the side channel attack that we might be worried about? So again, a very simplified view of it. So suppose you were trying to multiply these guys. You would basically multiply 0, multiply 1, multiply 0, multiply 1, and you get this result. But looking at this, you might say, you know what? These 0 steps are completely redundant. I can maybe just completely skip them. So if the value is 0, I just kind of skip it, and I just keep going, just shift left and add. Okay? And if this means that at every point you're testing whether or not the value here is 0 or 1 and doing something special. Now, this is a trivial case, but of course, you can imagine optimizations like this. Now, this does make the code faster, actually. Not twice as fast, but 1.5 times as fast. But it leaks information, because now the runtime of this is telling you how many ones there are in the second argument. And a priori, you might say, nah, the number of ones may not give me that much information. But if you are able to repeat this, you can actually recover an entire secret key. So there's a whole bunch of papers where people take a 1-bit leak somewhere, and they can expand it out into a leak of an entire secret key. So this is the kind of side channel attack that you want to avoid. So however many optimizations you're doing, you cannot do optimizations that depend on the value of a secret. If your optimization is secret dependent in any way, you're most likely in trouble. There are other ways you could be in trouble too. This is not the only way, but that's definitely one of the predominant ways in which people introduce side channel attacks. So how do we implement and verify that our implementation of modular multiplication is correct? So you can go look at the Hacklestar repository, which shows you one way of doing it. So in Hacklestar, there is what we do is we write implementations of crypto algorithms in F-star, actually in a subset of F-star that's called low star. If you want even better performance and want to write things in assembly, you can write the code in Veil as well, and that's its own project. And both of these could meet the same low star interface. So that's the low star interface for modular multiplication. So what this says is that there's basically an output buffer. These are the two input values we're going to multiply. The prime is already known, so you can ignore where the prime is. This is just a temporary scratch buffer we're going to use. And it's going to basically put the output over there. That's going to have the output. So in order to verify this code, we need a bunch of preconditions. These are all the memory safety preconditions that says which pointers are live. All the pointers must be live, which means they must have been allocated. They must have the length that we think they have in the current heap. And they all must be mutually disjoint. Well, you can be a little bit looser here. They don't actually have to be all mutually disjoint, but this is a simplification. So they all the buffers have to be mutually disjoint. They should never even overlap, okay? They could be like completely separate. And in that case, we want to prove that, in fact, the output only modifies out and the scratch. It doesn't touch F1 and F2. That's that condition. And this is the functional correctness guarantee, which says that the output, if you evaluate the integer which is stored in the output, it is basically the integer stored in the two inputs multiplied modulo p. So that's what the spec says. So the spec says basically this is the mathematical input-output behavior of this function. So this is your full spec of what modular multiplication should be doing in low star. And we have two implementations of it that we prove actually meets the spec. Okay, actually, we have three implementations. Okay, and those implementations do all kinds of optimizations. One of them is in assembly, right? And one of them is in C, but still is trying to do things as fast as possible. So looking at this, you can already tell where the burden of annotation and the burden of proofs are, even if I have not shown you how the proof works. You can see that the memory safety annotations are kind of annoyingly big, right? But okay, but following that, with a lot of blood, sweat, and tears, we built an entire library with a whole bunch of algorithms, pretty much every modern algorithm that you want. Okay, so it's not just a demonstrator on one algorithm. No, it's like all the algorithms that people use in TLS were written, verified in low star, some of them in Whale, optimized as much as possible, some of them with SIMD optimizations for different platforms, everything verified. Okay, and that generates code. It's written in F star, verified in written in low star, verified in F star, and it generates C code, and today it also generates Rust code. And it's widely deployed. But the effort is huge. So it's 250,000 lines of F star, which generates about 130 lines or 30,000 lines of C and assembly. And it burnt 3 PhDs, I would say, or maybe a bit more. And I do use the word burnt kind of, none of them is in research anymore. And a lot of the effort there was not just building the proofs, because building the proofs the first time around was easy, well, systematic, not easy. But actually, you have to maintain the proofs as F star evolves, as Z3 versions change. If a proof is flaky on one place or another place, or somebody says, oh, we have to run this on Spark, so you have to add this one implementation detail somewhere and then re-verify everything. And that proof maintenance is actually both psychologically and physically quite a lot of work, at least for researchers who are, we have published the paper. Why are we still taking care of this library which is 10 years old, right? So, but okay, success, let's say. Lessons, well, also because we did a lot of work on trying to deploy this code in real world places like NSS and Firefox and other places, we learned quite a few things. Like, first of all, you can't just say, hey, this is verified, take it. They'll ask you what the performance is, and if the performance is 5% slower than what they have currently, they're not going to take it. Nobody's going to use it, right? So it must match the unverified code. If you can exceed the unverified code, you have an excellent argument. And in some cases, you can. Because like I said, you want to try to delay the reduction, avoid the carries, parallelize things. There are many places in this kind of code where you go and look at it, and there would be a comment by the developer saying, I think this particular carry is not needed, but I'm not sure, so I'm going to leave it in. Because it's always OK to do a conservative operation like that, but maybe it wasn't needed. But if you have verification, you can sometimes prove, in fact, that particular carry or that particular reduction was not needed and eliminated, and now you're still safe, but you're faster. So this is why a lot of verified code, not just in Hacklestar, but also in Jasmine, also in Whale, is sometimes faster than the unverified code it was inspired by. Because with verification, you can actually show that certain operations were not needed and remove them. The other requirement is that your code that you produce, because in our case, we and most of the people in this field are not directly verifying code that users wrote. We write code and we generate C, we generate assembly. And we say, hey, please use this assembly in Chrome or in Firefox or the C. So when you're giving people this code, they, of course, like the fact that it's formally verified, but they don't understand formal verification or what the source code. They're not going to read the F star. They're not going to read the coq. What they're going to read is the output, which is the C or the assembly. So it has to be reviewable. It has to be well commented, has to have nice variable names, has to have the right structure in a way that they can review it as if a human wrote it. Okay? So that actually creates a lot of pressure on the tooling to actually produce code that is actually readable, because of course, it's much easier to produce code that is correct but not readable. And the other place where a lot of requirements come in from the industrial side is that you might say, hey, I've done the RFC, I'm done, I'm gone. But in fact, the way people use cryptographic algorithms, they use a lot of flexible APIs, and they want to run it on many more platforms than you might have tested it on. So there's a lot of work that is around the cryptography, which is kind of at the edges, in the interfaces, which is actually needed before this can be deployed. And on the crypto proof side of things, well, as I showed you in that thing, the memory safety annotations kind of dominate the specification effort. Proving them usually is quite easy, especially since you're using F-star, which is an SMT solver, which is particularly good at proving the kind of memory safety preconditions that we need to prove. But still, it takes a lot of manual work to actually document all of these things. And SMT automation is crucial, but except when it isn't, right? So the Everest retrospective has a nice discussion on this. We find that there's most proofs that we send to SMT are done in milliseconds. But there's a few proofs that might take hours. And so the cost of a verification run is dominated by a few fragile proofs, which you can rewrite in a way that the SMT solver will like. But if you don't do that, if you don't garden those things well, in fact, most of the time you're spending just fixing these 5 proofs that keep breaking every time. OK, so taking the lesson from that, we don't do that anymore. So in Crispin, we don't actually write F-star. We write all our crypto now in Rust, and we verify it from Rust. Okay? We still use F-star, but we only use F-star as a proof backend. We don't use it as a programming language. And this is primarily so that the artifact that we are verifying is an artifact that crypto developers can write. And even if they don't want to write all the proofs, they can read, right? So that's kind of particularly important. So the example here is post-quantum crypto. So that was our excuse for doing this. So there's a new set of algorithms that everybody is implementing now. And we implemented one of them. We have this tool chain called Hacks, which takes Rust code and then compiles it to F-star. Okay? So you can do the same kind of thing that you were doing in Hackle-star. Have a spec in F-star, derive the F-star model from Rust, have a spec for all the Rust libraries that you're using, throw it to F-star, try to prove that it's correct, and then use it. Notably, since Rust is already giving us memory safety guarantees via the borrow checker, we translate it into purely functional F-star. So we throw out all the memory safety preconditions, postconditions. We say, we are trusting that the Rust type checker and borrow checker are making sure that things are memory safe. We don't have to do that. We only have to talk about runtime safety conditions and correctness. And that big simplification. Of course, most people don't still want to use Rust. I don't know why, but there are people who can't use Rust in their systems. And so to support them, we do have a tool called Eurydice by Jonathan Protsenko that takes that Rust code and compiles it to C code. It's kind of weird, but we do it because it's easy for people to use it, whatever. So what does this look like? Well, if you write a reduction algorithm in Rust, this is actually a very simple reduction function. It's called Barrett reduce. It's used in post-quantum crypto a lot, where you take a signed 32-bit integer, and you're basically doing the modulus of that integer with this field modulus, which is the number 3329, a very small number. But you can't just call the modulus function, because that's not constant time. So calling a modulus function on most platforms will leak the argument. And this is a secret. You don't want to leak that secret. So instead of doing modulus in like a sane person would, you actually do all kinds of shifts and multiplications and additions that you know are constant time on most platforms. And this is how these things are usually implemented. So this is actually just you could do this one mod, but you can actually do this like this. So what can go wrong here? Well, we said Rust is memory safe, right? So it can't really throw a sig fault, but it can have runtime errors. So that multiplication, that addition, that subtraction, that multiplication could overflow. So and in Rust, those operations in debug mode, if you run them with very large values of the input value, it will basically throw a panic. Okay? At runtime, it won't throw a panic. It will just do the wrapping operation, give you the wrong result. But either way, both of them are bad, right? So you do want them to panic if they're panicking. So you want to prove that these things will never overflow, okay? Because that's the intention of those functions. The other thing that you want to ask is whether it's producing the right result. So for both of them, what we do is we add contracts to the Rust program in Rust. So the requires basically says that as long as the value is between this negative number and this positive number, when you're doing signed arithmetic, it's all very kind of interesting. You have to always think about the negative and the positive. Then we can guarantee that the result will be between the minus field modulus and the plus field modulus. And the result modulo field modulus is in fact the same as the input value modulo field modulus. So this is a spec of Barrett reduction. So this is the functional correctness spec, and this bit is what you need for panic freedom. So under these conditions, you take that code, translate it to F star, and say, hey, can you prove to me that none of the arithmetic will ever overflow? And can you prove to me that this post condition holds? The SMT solver is able to prove it completely automatically without any annotations. Okay, so for 32-bit integers, there is enough information in the SMT that it can actually do this automatically. We also did these kinds of proofs manually in Rock, in Lean, and so on, and it can sometimes take hundreds of lines of proof. So this is a classic place where SMT is doing the right thing. Of course, it's very fragile, so a small change and maybe it's not going to do the right thing. Then there is secret independence. So we want to prove that, in fact, none of the operations is going to leak secrets. So we kind of have a notion of secret integers on which you're only allowed to do certain kinds of operations and other operations are forbidden. And that basically prevents a lot of the leaks that can happen at the source code level. But note that we are at the source code level. We don't know what's going to happen at the final target code level. But even so, at the source code level, we can find attacks. So while verifying our Rust implementation, we found a place where we were doing a modulus operation, actually a division with a constant. And on the left-hand side of the division, there was a value t, and the value t was a secret. We're saying we're doing secret divided by something. And according to our rules of secret independence, this might leak the value of the secret. So we fixed that, and then we went and looked at the other implementations, including the reference implementation of the standard. And in fact, the reference implementation had the same issue. So this, then some other colleagues of ours showed that this bug can be expanded out into a big attack, and that became known as the Kyber slash attack. And that's kind of, that was a paper at Chess this year, won a Best Paper Award and so on. All we did was to run our tool to say that there is a bug in our code, and this bug seems to be in other code. All the rest of the work, which is really hard, is done by the cryptographers. But this shows that already with these kinds of type-based analyses at the source level, we can find interesting things. We just said we can't be sure we have found all the things. So libcrux exists. You can go try it out. It has optimized portable implementations of MLChem and MLDSA. It also has Rust implementations compiled from Hacklestar for all the other algorithms you looked at earlier. So it's a pure Rust crypto library with decent performance, I would say. And it's already deployed in Firefox and Signal and so on. What lessons can we take? We're still not done with crypto, but I would say crypto verification is kind of almost a solved problem, as in it won't be surprising if you tell somebody, hey, I verified this new algorithm. That shouldn't be surprising anymore, but there's still interesting questions left which are open. The first thing is side channel analysis. So we are doing some very weak side channel analysis at the Rust level, but really between Rust and the time when it's actually getting executed, there's a whole bunch of side channels that might be introduced. The compiler itself might introduce some side channels. Plus, there could be speculative execution problems at the microarchitecture level after even we get to assembly. To address this, we need very precise machine models. We need specialized tools. We might need support from the compiler on how to compile crypto code and so on. So it's an open question. Lots of people are working on it, thinking about it. There's a whole session on it today as well in one of the other conferences, I think. And so this is an interesting but open area. Of course, there is the alternative, which is write everything in assembly. And for some people, that is actually the right solution, because they really care about crypto. They want to write all their crypto in assembly and verify it in assembly, so they have full control about where things are, and they can run a lot of tools directly on the assembly code. I find that depressing, because it's been so long that we've tried to build these compilers, and now to say, all right, maybe AI will make that easier. The other thing I think is that anything that you do like this has to fit into the developer workflow, right? So, I mean, we can write code, yes, sure, but we shouldn't be the people to write crypto code. We are like formal verification people. The crypto developer should write the crypto code, and we've had trouble getting them to write things in C, even in F#, F star, Coq, that in a way that can be verified. With Rust or domain-specific languages like Jasmine and Whale, there's a better chance. The people that crypto developers are willing to write and use these nice new modern languages to write their code in a way that can be verified. And of course, the last thing is that verification still obviously is only one component in the larger ecosystem here, because a lot of things, there are a lot of edge cases to the verification where we are not proving things, and we need testing and fuzzing to fight those things. All right, so we talked about crypto, but really a lot of the interesting things are at the protocol layer. So we talked about TLS and said, oh, there are so many attacks on it. So there was this whole effort on standardizing TLS 1.3, where the entire community came together and they said, hey, you know what? We're not going to standardize this new protocol until the academic community comes and does proofs and tells us that this is actually secure. So a lot of these proofs are pen and paper proofs, the ones in black, but the ones in green are actually machine check proofs that people did. And they were highly regarded. So people were waiting for the machine check proofs before they standardized the protocol. So in a way, this was kind of successful. The ones in red are the ones where actually important attacks were found on the protocol and then fixed. So obviously, the latest ones hopefully did not have any attacks. And so this was like the most analyzed protocol ever. And this is basically a complex-ish protocol, but still fits on one page. So it's not terribly difficult, but still it was quite a lot of work. And in our group, in Project Everest, we developed this implementation called MeTLS, which over time covered many different modes of TLS 1.0, 1.1, 1.2, and 1.3. And it's a pretty large project. It lots and lots of modules. It models all the state machines, also precisely implements all the message formats. It's a reference implementation, so it has to be interoperable with other implementations of TLS. Use verified crypto, like we talked about from Hacklestar and Whale. And it's a major effort with lots and lots of researchers, more than 30,000 lines of protocol code in over 100 modules. And what's interesting, perhaps, is that when you talk about protocols, unlike cryptographic algorithms, which are mathematical functions, so the specs can be very succinct, when you come to a protocol, like I showed you in the previous slide, the spec of the protocol can itself be very large, I mean, almost as large as the implementation. So in some cases, a reference implementation is as good as the formal specification, if you write it in the right language and so on. And let's forget about C, but if you can write a reference implementation of TLS or MLS or Signal in Lean or whatever language you like, it probably serves as a good spec, okay? But this is big, so the implementation is big. The nice thing is it helped us find attacks, and while developing this and while verifying it, we found quite prominent attacks, and it influenced the design of TLS 1.3, but it was a lot of work. What we learned from it was that, well, you can't just focus on the crypto, because a lot of the issues, verification issues, as well as bugs, as well as things that people actually care about, are outside the crypto. They are in protocol message formats, they are in state machines, they are in things which are classic software verification things, but interacting with crypto in interesting ways. In particular, there are things like downgrade attacks that only appear if you model two different versions of the protocol and enable them both. Then you have to worry about how they interact with each other. If you verify just them in isolation, you would not see these attacks at all. So the more you can put into your implementation, the more attacks you'll find. And verifying a reference implementation is a way to ensure that we captured all the details. The other thing we found is that when we were trying to do monolithic, all-in-one proofs of security, correctness, memory safety, all in F star in the same model over the same artifact at the same time. And this was okay for small protocols. At the level of TLS, it was not scaling. It just wasn't. It just took us way too long. We never finished the full proof for the whole thing. I would say that part of it was a failure. And while doing this, we discovered that, well, there were different ways of doing proofs for the different things that were working. So for memory safety in low star, that was kind of working. The annotations were big, but it worked. It was quite easy to automate. For cryptographic security, a whole new technique called state separating proofs was developed, which was then embedded into F star, but also had its own tool called SSProof. For parsing correctness, a whole new tool called EverParse was developed. And these are all different ways of verifying different parts of the problem. They were all embedded in F star in a way that they could talk to each other, but they were kind of completely different verification techniques. So taking those lessons to heart, we don't do that anymore. So at Crispin, we recently built a TLS implementation just as a demonstrator at CCS this year called BERTI. And it's a post-quantum version of TLS, so it's TLS plus also some post-quantum cipher suits. and it's open source. You can go download it and whatnot. And when verifying Birdie, we now use the hacks methodology again. We take the Rust code for Birdie, we take hacks, and for certain modules, we produce F star. For certain modules, we go to SSProve for the cryptographic core. For certain modules, like the protocol modules, we go to ProVerif. And we prove different properties for each of these. For some modules, we actually analyze them in 2 different ways using 2 different tools. And of course, the crypto itself comes from libcrox, which is formally verified, so it's on the side. Okay, so these are 3 completely different techniques for verifying different kinds of properties. In fact, not just that. So we use the Rust type system to enforce state machine linearity, and we use all of these different things. And we were able to do this entire work in about a year, including the implementation, including all of these other proofs, and so on. So we felt that that was the right level of effort for this kind of project. This is not as comprehensive a result as you can get for MeTLS. It's not all in one. These are completely different proofs. There's no single formalization linking them all. So there are weaknesses. But pragmatically, we were able to prove a lot more of the properties we cared about using that methodology than if you went for a single unified one. All right, so the last part of my talk is basically saying, well, what does all of this mean for future protocols, right? So what if some company comes to us and says, and this is what people do with Crispin, and says, hey, we have this completely new protocol we want to deploy. Can you help us formally verify it? Okay. So in this world, I'm going to take the case study of Signal, who we've been working with for the last year. And if you know anything about how the Signal protocol works, whenever you open a new Signal conversation with somebody whom you have never talked to before, by the way, Signal is the same protocol is used also on WhatsApp and Facebook Messenger and so on. Okay, so it's the same protocol, but I'm talking primarily about the Signal messenger here. So when you want to send the first message, it does this protocol called X3DH. What it means is that you're going to take your key and the other person's keys, and you're going to mix them with like 4 different Diffie-Hellman computations and get a key. And once you have started conversing with each other, with every message, you're going to refresh the key. And this is called a double ratchet. Okay? And this kind of protocol is state of the art. I think people strongly believe that this is the right way to do messaging. This is why WhatsApp uses it, Facebook uses it, and Skype, when it existed, used to use it. And it gives you very strong guarantees. So some of the strongest guarantees, even stronger than TLS, because it gives you post-compromise security, which is that if somebody takes away your phone and then gives it back to you, and you continue your conversation, within a few messages, you will recover your security, even though that person who took your phone has learned the messages they learned at that time. They cannot interfere beyond the time when you got your phone back. So this is kind of important for many kind of whistleblowing type situations. There's also like some effort at providing deniability. I don't particularly believe that that's a very useful guarantee there, but let's ignore that. So that's the classic protocol. So last year, 2024, Signal decided that they wanted to make their protocol post-quantum secure. And post-quantum secure in a particular sense, that if somebody were to download all the Signal messages sent from anybody to anybody today and store it, and waited 10 years until a quantum computer came along, and then they tried to decrypt everything, they shouldn't be able to get all these messages. Okay? With classical Signal, they can. So you store all the messages from Signal server 10 years from now, if you believe that a quantum computer is coming in 10 years from now. It's up in the air. You will be able to decrypt all of those messages. And some of these messages may still be sensitive 10 years from now. So, but to avoid that, what you can do is you're already doing the 4 Diffie-Hellmans. Keep them, because that works. Everybody likes that. Let's add a post-quantum crypto construction in here. So now we have these 5 secrets. Earlier we had these 4 secrets. Now we have a 5th secret coming from post-quantum, and mix them all together. So it's purely additional, right? So we had 4 secrets. We're going to add a 5th secret, mix it together, and put it into the protocol. So now we have post-quantum spice on top of our Signal soup. And yeah, so the protocol itself, this is what changes, this changes, but most of the protocol can remain the same. Okay? And this for them was very important, because they really live on their reputation. And their reputation is that their protocol is good, and they don't take influence from any government, and everything is open and transparent, and they can show that, oh, look, we only added some things. So it's a very small edition. It should be very easy to analyze. So they published this spec, and I and my colleagues were like, hey, let's analyze this, just as a kind of a weekend project. because we already had models of the old protocol. So we're like, hey, let's model the new protocol. So we want to check that the new protocol is at least as secure as the old one, because it's additive, right? And that it's secure against certain categories of quantum adversaries, because that's the whole point of post-quantum crypto. So what we did was, of course, we wrote down the protocol spec. We added a compromise model, security goals, cryptographic assumptions on what actually we assume about the protocol. And then we ran this tool called POPL'26, which is a domain-specific tool for doing protocol analysis on this protocol specification. And whenever if you found an attack, it could mean that, oh, actually we modeled something wrong, or it could actually mean that the protocol is broken. And once you have found all your bugs, you might then say, hey, you know what, I want to do actual crypto proof, like a pen and paper cryptographer proof. And for that, you can use this tool called CryptoVerif, which uses the same input, but actually can do crypto proofs. That's the idea. If you're curious about what these things look like, the specification of this thing in POPL'26 looks something like this. So it's, you know, it doesn't matter, but the syntax is not so shocking. The Signal developers were able to read and edit these scripts, okay? And then if you press the button and say, ask POPL'26, hey, can you prove that this is post-quantum forward secure, this is a query which asks that. It's a very weird syntax, but hey, you know, whatever. You can think of it as like a safety kind of temporal logic type formula. It's called a query in POPL'26. And if it doesn't hold, POPL'26 will give you an attack trace. Again, the attack trace takes a little bit of brains to figure out what it's doing. Apparently, Claude is very good at interpreting this and giving you very nice. So we don't need to make better tools anymore. We can just ask AI to explain what the bad results of our tools mean. So it can actually explain to you quite nicely what this means. So I'm not going to even try, because I can't do as well as Claude for this. And once you're done with those, you can actually take the same model and write this is kind of a pen and paper crypto proof. It's called a game-based proof, where you say, I'm going to treat the initial protocol as a game between the attacker and the protocol, and I'm going to describe a set of transformations, which are each of them is justified by some cryptographic assumption, and the final game that you end up with is going to be trivially secure. Okay, so that's kind of the style in which you do these proofs, and this is a CryptoVerif proof of that protocol. Again, I'm rushing through this. If you have any questions, I'm happy to answer. Right? So, and then, of course, we want to model a quantum adversary. And of course, it's hard because the quantum adversary doesn't really exist. So most of us have ideas of what the quantum adversary could potentially do. But every second week, there is a paper that tells us that the quantum adversary's powers might be more or less than what we thought. So it's a very fuzzy area right now. But OK, at least what everybody agrees on is that when the quantum adversary finally appears, Diffie-Hellman is kaput. We can't use Diffie-Hellman anymore. So that's for sure. Everything else is a bit unsure, but OK. And that symmetric crypto is kind of good. Symmetric crypto is good. Diffie-Hellman is bad. That we can agree on, for sure. So for POPL'26, that's basically what we do. We basically allow the attacker to break. There's a quantum apocalypse after which it can break all the asymmetric crypto, but not post-quantum crypto. And then CryptoVerif has a special mode to exactly prove properties even under passive quantum adversaries. So we use that. So using that, we can then try to prove the thing. And while proving it, we find a few attacks, bugs, vulnerabilities, attacks. One of them, which is the easiest to explain, is this one. Look, I said we're just going to add this one thing here in the protocol. This one thing is actually signed by B. That's what this curly bracket means. But in the protocol, there was already another key there, which is a Diffie-Hellman key, also signed by B. So, well, what if the attacker took that signature signed key, put it here, this signed key, put it there? Then you, when you are creating a first message with this person, are going to use this one as a post-quantum key, but it's actually a 32-byte Diffie-Hellman key. And this one as that one as a Diffie-Hellman key, which is post-quantum, and this one as a post-quantum key, which is actually a Diffie-Hellman key, and all bets are off. Okay, in reality, one of them is a 32-byte key, and one of them is a 1 kilobyte key. So most implementations will basically crash rather than actually do the computation. But the spec does not say that, in fact, they should all be this size. So it's possible that there is an implementation that will pass this, and then all security bets are off. So this is a classic protocol flaw. Right? This is a confusion formatting flaw, very classic. Lots of people could find this before. And POPL'26 obviously can find this kind of attack, and found this attack, and found some few other weaknesses. And this is representative of a general class of problems that comes up. And this is the kind of thing that, one takeaway from that is that whenever you have version 1 of a system, tomorrow you're going to have version 2 of the system. They both have to live together, most likely for a long time, but even if not, at least for a month or two. And in that period, you have to be very careful about confusion and cross-protocol attacks between version 1 and version 2. A lot of flaws come from there. And an immediate fix is that make sure that all your formats are very, very explicit and disjoint between these versions. And of course, there are nice frameworks, including the one by my student called Comparse, which can guarantee that you would have this property. So with PQXTH, what happened was our results, we told them, hey, look, there's a bug. They fixed the bug. They pushed out a new specification. We proved that the new specification was we formally verified in both ProVerif and CryptoVerif. And they basically said, OK, we're done. And this whole process from the first version, verification, new version, was 1 calendar month. So I think that's kind of, for me, always a big marker of success, that somebody can come, use these tools, and do things in a month. I mean, not somebody, we did, but. So the Signal team was impressed enough that, in fact, for the next protocol that they deployed, which is now in all your phones if you use Signal, which you should, it's called the sparse post-quantum ratchet. It's it was formally verified from the very first moment that they started even sketching it. They verified it in ProVerif using some of the models that we provide them. And then as they started implementing it, and it was in parallel, things are never like beautifully phased, right? They started implementing it. They used hacks to verify the code from the very beginning as well. So this is part of their CI. They run it on every check-in. The developers write the annotations. Often they need advice from us, because hacks is not such a great and usable tool, but they're nice to us, and they kind of tell us when it doesn't work. And so in collaboration, this is actually running right now on Signal CI. This has become part of their workflow. You can read about it in their blog post. And we are basically using the same thing we did for Bertie. We use hacks. We extract F star to do some kinds of proofs. We extract ProVerif to do other kinds of proofs. All right, final set of lessons. When interacting with people like people from Signal, who are real developers, crypto designers, and so on, and we want them to use the tool. We don't want to build this whole thing and give it to them because it's their stuff. The choice of programming language and specification language is crucial. So Rust is very attractive to a whole set of programmers. They're much more accessible. But also the specs, if you told them, OK, you can write Rust code, but the specs should be written in this weird custom language, even that's not doable for them. They can't, somehow there's a blockage there. So if you can write your specs also in Rust, good. Or if it's in a special annotation language, you really have to work hard on making that really accessible. Using multiple provers was great for lowering the verification effort. But of course, big caveat, we are not getting an end-to-end security result like we were aiming for with MeTLS and so on. Because these are 3 different tools, 4 different tools. There is nothing formal linking them. Okay, so it's a very pragmatic approach, but not really a foundational or compositional approach. Concluding, I hope I have shown you what exciting things people have been doing with formal verification and real-world crypto. Today, there's verified crypto libraries in all major web browsers, and hopefully soon in all major operating systems, and verified implementations and designs for many prominent protocols. Even Apple's PQ3 has a formal verification in it. It's become kind of default for new protocols, I would say. The next challenge is, but this is all done by, this is all done by people like us, right? We write the stuff and we give it to them. And that works only up to a certain stage. It doesn't really scale. We really need them to use the tools, right? And especially for cryptographic developments. So making that usable is a challenge. Rust and some languages, domain-specific languages, can help bridge the thing, but there's a bunch of open work there. And the last comment I would like to make is that there's this big thing going on right now, which is the post-quantum crypto transition, where everybody is changing their cryptography to be secure against quantum computers. Whether or not you believe in quantum computers or whether this is a good idea or whatever, this is a great opportunity, because they're all upgrading. Basically, every crypto stack in every device, every hardware, every software is being upgraded everywhere. I think we should use this as a stealthy moment to push in verification everywhere, right? Even if you don't care about the quantum adversary. And that's what we're trying to do, and I think everybody should be doing this. Anybody says, hey, we want to do quantum, we say, hey, verification. Yeah. So anyway, so that's that, and I'm open for questions.
We have something like 10 minutes for questions, and we have a mic. If you have questions in the audience, because 2 mics even, because we have the recording and the streaming. So please raise your hand for questions.
Hey, very nice talk. You said that nowadays you sort of write your protocols in Rust and then sort of trust the Rust type system to do sort of the right memory safety things and then only verify the rest. But then you also said because people still use C, you have some compilation to C. Which memory safety guarantees for C do you get?
C Lite, which is the internal language of Caramel, which is very similar to C Lite as used in ComSert. And then we use the same Caramel toolchain that we were using in Hackle Star and F Star, Low Star to translate it into C. So, so the argument, and this is informal, is that the Rust code and the C Lite code have the same behavior, even though their memory models are quite different, because we are in a very restricted sublanguage. So we're going from a very restricted sublanguage to a very restricted sublanguage. We're never in full C, actually. We're still in Low Star, let's say. And so from that point on, we get the formal guarantees of Caramel that were verified in SEFP, whatever. But this first stage,
So you you were saying that at the beginning you are doing like proofs, like you were taking proofs on models and then you are translating them to code, but then you switched to looking at the code and then translating them to models. And actually in the end, like you said, that this also has some limitation that, okay, you don't know like what's exactly proved in the end. And actually, indeed, like when you do the translations, like, I don't know, translation to ProVerif or to F star, or like I imagine like those translations are not ideal. Like if you would write directly the model in ProVerif, it will write maybe even a more realistic model, because I don't know, in a I don't know, some ProVerif experts, they know, okay, this causes problem. So the question is, okay, I don't like, and then I think you also asked the question, but you didn't provide the answer. Like when you have a new protocol, like what is really what should be the workflow? Because for example, if even in Signal, like the protocol changes, do I really need to rerun this, like your tool, the hacks, or like do I need to first maybe rather look if I want ProVerif, if the protocol changes, then I do the changes on the ProVerif model. If the crypto changes, then on the SS-proof model or so on. Yeah.
question. In fact, Signal is the perfect answer for this, because in Signal there is actually like a one person, really maybe two people sometimes, who do the protocol design, and it's always been like this. It's an important protocol, but one or two people do it, and then there is like 3 or 4 people who do the implementation. Okay, and the 4 people doing the implementation are less expert, I would say. But so the designers directly want to write ProVerif. They enjoy writing that, so they've gotten hooked, let's say, like many of us have, right? So for that it works, right? So because then, yeah, they would actually go and actually write the ProVerif, re-verify it, verify the properties that we together came up with, but they would re-verify it. And if something fails and they don't understand it enough, they might ask us or Bruno or somebody else who's an expert, saying, hey, can you help us? But they're willing to use the tool directly, right? But the reason for doing the hacks thing is different, actually, because they are worried that during the implementation, they may have, because they have a fairly complex state machine, they may have messed up something, so that in fact the protocol as implemented is not exactly the protocol as they designed. So so there are 2 choices there. You can either prove conformance between these two, but proving conformance between distributed programs is kind of a bit annoying. So rather than doing that, we say, hey, you know what, just directly do the verification again on the code. So it's kind of a different verification. It's more like sanity checking. And you're right, the model that comes out of there is not nearly as nice as the one you can write by hand. But we try to make sure that the same properties are proven for that as well.
So have you tried to do any of this verification effort with Dafny, or is there a comparison you want to make between the capabilities of Dafny and F star? Yeah.
So of the work that I showed you, Veil has been used with both F star and Dafny. And if any of the Whale people were here, they could give you a, hi, yeah, of course. Right, sorry, you guys can give a proper comparison maybe later on as part of your question answer. But we primarily use F-star. I have some experience with using Verus for similar things, which again has a similar feel, let's say. But I can't speak specifically to Dafny.
Maybe a related question because about this F-star, because my understanding, like I don't really know what it does, but like it's proving functional correctness for you, like type of properties. So, like why, like presumably you could prove some of the same properties with Verus directly or with other like SMT-based tools, like so. And like what actually, can you just, for us who don't know, start brief summary of F-star and what?
So HAX has a different kind of philosophy than Verus, in that rather than using the one true SMT solver pathway, we are a bit agnostic and we say, hey, you can use any number of tools. We even have a lean backend, we have a ROC backend, F-star backend, and then on the security side, we have an SS-proof and a ProVerif backend. People are interested in building other backends. So the idea is, depending on what proof you want to do, you can write the right annotations and guide it towards that tool. So some of the proofs that we're talking about, like functional correctness, you can definitely do with Verus. You can also do with NAS, which is a tool by Sean Ho and Jonathan Podzenko and so on. And they're kind of close collaborators of ours. So there are many tools, even Creusot, whatever. You can do these functional correctness proofs there. There's the panic freedom proofs that, again, all of these tools can do. We have nice comparisons between all of them as well. But here, we are primarily focused on the crypto side of things. And there, we want to interoperate with things like Hacklestar, with some other kind of, there's a whole framework called DeviceStar for doing security proofs in F-star. And there's a whole bunch of these things which already exist in F-star. So for us, being able to interoperate them with them is valuable enough that we go to F-star. But if you were willing to re-implement all of these things in any, like in Lean or in Dafny or in whatever, then yeah, we could go that way.
I have a question on the transition to PQC. So there's a number of companies now offering the services to deliver PQC-ready libraries, crypto libraries. And so you do that too. So in competition with them at Crispin. And some of these other companies, they also use formal verification, but very few in fact. So PQ Shield, for example, uses some formal verification. But most of these...
So I can't tell.
They advise that, they advocate for that on their blog, but yeah, we don't have the source code. But for sure, most of them don't use formal verification. And so how do you see formal verification really making a dent here? Like you said, that's an opportunity. How is it going to materialize? Do you see other players than you pushing for that?
So in fact, PQC is, we did our work on libcrux was funded by Google, and the idea is that hopefully Boring SSL will adopt the code that is coming from us. But it's still an open question. I know for a fact that Microsoft is working on its own SymCrypt, formally verified post-quantum crypto library. So they're going to do that using NAS. They are doing that. Maybe have already done a chunk of it. AWS LC uses a combination of CBMC and Isabelle to verify their post-quantum crypto. So Apple is not making too many noises, but maybe they will also have formally verified crypto in the future because they've hired some formal verification engineers recently. So I can totally imagine this becoming like the default, actually. So when we are trying to tell people to use our library, we don't actually sell it. It's open source. We don't believe that formal verification should be a selling point. I think it should be the default. Right? So what we give to Signal, for example, why they use libcrux is that in their new protocol, they needed a new API for doing MLChem in a kind of a novel way. It's actually interesting in that MLChem braid. And we were able to implement and verify this new API for them and deliver it to them. So I think the functionalities are what we should be pushing, and formal verification should be default. It's not yet the case, I agree. But I don't see a future in which people should be using non-formally verified code. Of course, you also need testing, you also need FIPS certification, you need a bunch of other things, but this should be the baseline, I think.
Hello, Nice talk. I want to ask a silly question. So, do you expect like artificial intelligence, like large language model, can mitigate the proof effort of cryptography? Because I assume so what I understand is that the proof effort of cryptography, like for TLS, is really, really huge. But do you think there is a chance, or like how much effort can be saved with the help of large language models these days?
Good question. I don't have an answer, but there's a whole bunch of people working on it. We are also investigating that. And it's unclear. I think there is a whole bunch of things like deriving annotations or propagating annotations that we do a lot of manual effort on, which should really not be done. And I use LLMs to automatically propagate things now. Ultimately, I believe that there should be a trusted proof checker that shouldn't be based on LLMs or AI, that can actually check the artifact that's coming out. And the way the artifacts are generated, you can use, whatever techniques that you want. And I think there's lots of people working on, like, you give me a big lean file full of sorries, I'll fill it up with proofs, right? And this is kind of a very common pattern, right? So that people are working on. And you can imagine the same to be done for large systems like TLS. I have not yet seen results that have shown that this is actually applicable at that scale, but it wouldn't surprise me if a lot of the proofs are automatable, not automatable, but fillable, let's say, using LLMs, and then should be checked using tools like the ones shown here.
So thanks you, Kartik. We'll have to stop here for the sake of our strict schedule. Thank you.
Can I start? Thank you. So in this talk, together with Rustan Leino and my team of students, Stefan and Roxana should be somewhere here in the room, we are proposing to add an interactive proof mode to the Dafny system, and the talk is about how we can do that. I'll structure the talk as follows. After a very brief introduction, I'll show you a running example of how a proof mode could be useful, and then I will demonstrate the proof mode that we propose from the user's perspective and briefly explain how it works behind the scenes afterwards. Okay, this audience likely does not need an introduction to Dafny, but just to make sure we are on the same page here. Dafny code looks typically like this. So each method has a specification with preconditions and postconditions, and then the code is typically annotated using some helper annotations, in this case some invariants, and the system at compile time, it verifies that the method meets the specification. And simplifying somewhat and skipping a ton of details, The way it works is that it gets translated into an intermediate language, into Boogie, which itself then translates the invariants, the specifications, into first-order formulae that are sent to an SMT solver, typically Z3. And you have here an example of what a verification condition might look like for the first invariant there. OK. This is all very nice when the code does verify. But when the code does not verify, things are less nice, because typically you have no idea where the bug is. Could be a bug in the code, in the specification, or in the helper annotations. And experienced users of the Dafny system, they work around this by building up some sort of mental model of what will the prover be able to prove, and then they will iterate in a code specify prove loop until they are happy with the result. OK, and I'll show you an example of how to develop a proof in Dafny for this lemma here, for this trivial lemma here, which does not verify automatically because it has some sort of nonlinear arithmetic in it. So it states that x times x plus 1 is divisible by 2. The system fails to prove it automatically. So an experienced user will typically start with a placeholder proof. So say assume false, so anything follows. And then later on, when it comes time to make the actual proof, you start iteratively working on it. So the first thing you might check is, well, does Dafny know that the modulo operation distributes over multiplication? You try this assertion here. You run the compilation again. And this assertion fails. So this doesn't work. You need another strategy. So the other strategy, you could try a case distinction. You could think about, wait, what happens if x is even or odd? And then fill in each of the cases separately. I'm sorry about this, but the pointer is not working properly. So, and then you can say, well, I'm working on the first case here. Does the prover know that x is 2 times x divided by 2? Yes, this does work. OK, and then you say, well, I'm going to help it now. I'm going to tell it that x times x plus 1 is 2 times something. OK, with these helper assertions, the first case goes through. And then the second case is analogous. So give or take, in roughly 6 steps, you end up with a proof of this lemma. But this development strategy has a number of issues. It is time-consuming because you typically need to recompile with each try. And you use the prover as a black box. You never really know what it can do or it cannot do. And also, the verification condition is not explicitly visible. So you sort of have to look throughout the code. What are the things that the prover knows? What does it need to figure out at this point? This is in contrast with interactive theorem provers like ROC or Lean. In ROC or Lean, you typically have the proof context at all times visible on the screen. So you have some hypotheses and the goal that you should prove. And then you guide the prover using tactics until you finish the proof. But the thing is that you receive immediate feedback. So you don't need to recompile the entire development. Of course, there are a number of disadvantages to interactive theorem provers that I won't go through. What we propose is to combine the two approaches by adding an interactive proof mode to Dafny. Now I'll show you how the proof mode that we propose works from the perspective of the user. When the user has a verification condition that fails to discharge automatically, such as the one that I've shown earlier, we want the user to annotate it using the IPM annotation for interactive proof mode. And then we start our proof mode, which is a Dafny script. When the proof mode starts, it presents us with what is known, the hypothesis, currently nothing, and what is the goal that we should meet. And it expects us to enter a tactic that helps create the proof. Okay, and one of the first tactics that we have is a tactic called check, which simply states, does Z3 know this fact, which is that the modulo 2 operation is distributive over multiplication. And when we enter this tactic into the proof mode, immediately, without recompiling everything, tells us that no, the prover cannot not prove this thing, so we need some other way around this. Okay, so the other tactic that we have is a tactic for case analysis. It is called case. So I'm saying do two cases, one where x is even, the other where x is odd. Okay, what happens here is that the proof goal is replaced by two goals. In the current goal, x is known to be even, and in the second goal, it will be the other case. Okay, and still we need tactics to discharge the current goal. Okay, the most important tactic that we have is the assertion tactic. So this works like assert in Dafny. What it does is it has this intermediate assertion that it proves from the current hypothesis, and then it adds the intermediate assertion as a hypothesis and brings back the original goal here. Okay, and finally, after all goals are discharged using tactics, what is interesting is that the interactive proof mode outputs Dafny code that can be copied back into the lemma. And the lemma, the Dafny code proves that lemma there. Okay. Currently, we support a limited number of tactics and commands, but we hope to increase this. Okay. Now I will explain a little bit how the proof mode works behind the scenes. And I have told you that in Dafny, typically the problematic verification condition is not explicitly visible. It's sort of, you can sort of recreate it if you look at the line that is failing the verification, but you can have some invariants that are known, some preconditions, and so on and so forth. This is not exactly true, because you can have Dafny output the smtlib file, so the verification condition that goes to the Z3 solver, by having it create the boogie file, and then from boogie you can generate the smtlib file using these two commands. And then the verification condition is visible, but it's not readable. So this is the verification condition that we see in smtlib for the lemma that I used as a running example. And you can see that it is polluted by this control flow construct, which is simply used for reporting back some errors, and by boogie. And then here there are a bunch of annotations about the heap, which are not relevant to the current verification condition because there is no heap. And then finally, the core of the verification condition is here. But still, it is not terribly readable because the arithmetic operations are not the smtlib arithmetic operations. They are functions, mod and mul, axiomatized to behave like the arithmetic operations. And then the variable name x is mangled. It is now x sharp something. And finally, the constants from the Dafny code are boxed using this litint thing. Okay, and the way the proof mode works is that it reads this smtlib file, and it translates back what we have here into Dafny speak. In order to do this, we have to use, we slightly augment the Dafny compiler. We have it create programmatically a number of helper functions that we call underscore protect something, which will help do the back translation process. So the protection functions, they work as follows. So when our version of Dafny reads up this lemma, it will protect every identifier with the right string, and this helps us unmangle the names. Okay, there is this protect to prove annotation, which helps us identify which verification conditions should go to the interactive proof mode and which should not go there. And finally, this protect scope thing helps us with name shadowing. And the verification condition is now even worse for a human being to understand, but all the information is there for the computer to extract back the Dafny code using Dafny speak. So the architecture of the system is here. In the initial Dafny code where there is an issue, the user should annotate the problematic verification condition with IPM. We run the instrumented version of Dafny, which adds the protection functions. We generate the boogie code. From boogie, we use stock boogie to generate the smtlib file, which we parse, and we back translate it into Dafny speak. The user interacts with the proof node, and during the interaction process, we do not call Dafny again and again. So there is just one call to the compilation pipeline, which is here. And finally, the proof is output. You can take a look at the proof mode. It's on GitHub. The goal is to support, in a faithful way, a large subset of Dafny. Okay. For the current prototypes, we take some shortcuts. So we support a very restricted subset of Dafny, which is ever increasing. And we have a bunch of hacks, like the way we parse smtlib or the Dafny expressions. And we also have a limited set of tactics and meta commands. But in future work, we plan on expanding this, so to handle a significant subset of the Dafny language, but in a faithful way. So what the proof mode can prove should be exactly what Dafny should prove. And I should say that the difficulty here is that Dafny is very monolithic. So it always starts with the entire code, the entire Dafny development, and generates all verification conditions, sends them to the SMT solver. So there is no incrementality in the Dafny compiler. So this makes adding a proof mode difficult. And we want not to run Dafny with every single command. We want our proof mode to be very fast. Okay. Obviously, the back translation process is, empirical. So we should empirically validate it on a number of examples. And we plan on adding some more tactics. And finally, of course, in the future, we want to integrate with some other tools, like the Dafny counterexample generator or the Z3 Axiom profiler. And ideally, the proof mode could be integrated into VS Code. You just could click and create the proof directly in the IDE. I think I am done with what I wanted to tell you. I'm happy to answer any questions.
Hello. Do you have an idea how to support rewrites? I don't see you have rewrites in. You can rewrite a sub-expression by like associativity when you're pushing.
You mean like a tactic?
Yes.
Yes. So we could add a tactic for rewrites. So currently we could support rewrites by doing assertions, but in the future it would be one of the tactics that we would like to support. We also plan on supporting calculational proofs as well.
Hello, thanks for the talk. It was very nice and very interesting. You have spoken about translating back from the VC level to Dafny level to print the VCs, but do you need another translator to translate whatever you put, for example, in an assert tactic to the level of the VC, or can you use Dafny directly for that?
So our current prototype uses a hack for this. So we parse it as a Python expression essentially, and we translate it recursively by hand into Z3. And we do this for a limited set of operations, so arithmetic and whatnot. But we plan on supporting a large subset of Dafny, a large subset of the Dafny expression language, but without calling Dafny at every step. So we have a number of ideas of how we could do this faithfully by using the Dafny parser, but in a very fast way.
So this without calling the Dafny at every step, I didn't quite understand how it works. Is that like if I, as a user, I introduce a new like assertion or a case, or like I want to use this tactic, I do introduce like some new Dafny code or something like, right? So how can you actually support that without integrating it into?
Construct in the proof mode. So for example, for the case tactic, we directly split the current verification condition into two verification conditions. For the case tactic, it's very simple. We add the first case implies the initial verification condition, second case implies second verification condition.
So you add it directly to the end, like to the compile.
Directly at the condition level. We work directly there in the proof mode.
Okay.
Let's thank the speaker, and that ends our first session. So we're perfectly on time, and we tend to keep at that during the day. So this means that we have 30 minutes break now with the catering at Hall 1 downstairs, and we'll be back here sharp at 11, because as I said, with these 18-minute talks and the AV that requires strict monitoring. Thank you.
Hello, everyone. So I'm Paul Pateau, PhD student at Université Paris-Saclay at Laboratoire Méthode Formelle, supervised by Jean-Christophe Filiatre and Andrei Paskevich. And today I will try to convince you that it might be useful to relax the rigidity of the abstraction barrier within auto-active verification context. But just before starting, let me recall some basics about auto-active verification to make sure that we are all on the same vocabulary. So here is a simple method, maximum, written in Dafny, which computes the greatest integer in the sequence of integer. And what you can see is the type of this method and the body of this method. But what you can't see is are the hypotheses that were in the programmer's head when he wrote this code. And here, one strong hypothesis is that the sequence given in parameter must be non-empty. Otherwise, it would result in a runtime error on line 1 of this definition. So what verification allows is to add some specification to this method, some precondition and postconditions to state the behavior we expect for this method, and then we can prove that the specification corresponds to the body of the maximum method by assuming the precondition and proving the postconditions following each possible pass at runtime. So we have this duality between assumption and proofs when we want to prove the functional correctness of a method. And on the opposite, when we want to prove a client of a function, then we will have to prove the precondition, and then we will be allowed to assume the postcondition. And the client does not have to know anything about how the method is implemented. And on the opposite, the method does not need to know how it will be used. And that's the tipping point of this duality is called the abstraction barrier. It is the separation between the client and the function definition. And I will present you how it is possible to relax this rigidity at the function entry. Sorry. So as you may know, Dafny does not do the proof by itself. It has first to compute, to translate the program into an intermediate verification language called Boogie, which will then compute a first-order formula that will express the correctness of the given program. And there are a lot of systems like Dafny. There is Prusty for Rust, Gobra, etc., which are all compiled into Boogie. There is also other intermediate verification language. For example, there is YML with another set of front ends. And today I will present a new intermediate verification language which is different from Boogie and YML, that are strict about the abstraction barrier, and we relax this constraint. So this is comma, which is already used by the Creusot prover. So in a few words, comma is a minimal intermediate verification language, which has not a lot of construct. We have function definition and application and logical assertions, and basically that's all. A comma program is written in continuation passing style. It is useful because it allows to encode many control structures within a small language, and also it simplifies the VC generator. And finally, we have what we call the explicit abstraction barrier, which is a keyword that represents the abstraction barrier that we will have to write explicitly in the code. And everything that will be above the barrier will be visible by the caller. So in the traditional way of doing things, it is only the contract of the function. And everything that is below the barrier will represent the implementation of the function that we want to hide from the caller. So let me give a simple example. So we want to verify the function Fibonacci in a comma. So we want to compute the nth Fibonacci number. So this is the first parameter. And as I say, comma is written in a continuation passing style. So we have an additional parameter which represents the continuation to which we have to pass to give the result after the computation. So it is implemented in the traditional recursive way. So whenever the parameter is negative, then we have an error. If n is less than 2, then in this case, Fibonacci of n is equal to n. And otherwise, we have to compute two recursive calls to compute Fibonacci of n minus 1 and Fibonacci of n minus 2, and then add them and pass it to the continuation. Now, if we want to verify this code, then the first thing that we have to do is to put somewhere a barrier. So just to start, we can put it just after the equal sign to hide the whole body to the color. And now we can add some specification. So as I say, everything that is above the barrier will be visible. So we want to make visible, for example, preconditions. So let's add a precondition. In comma, we don't need to have special construct for precondition because all the code above the barrier will be visible. So we have only assertions, and it is enough. So we want to assert that n is non-negative, and then we can add some post conditions to this function. But with the CPS style, we don't need either post conditions, but only assertions before calling the continuations. The post condition of a function is only the precondition of its continuations. So we can add some assertions before calling out, but here the call of out are below the barrier, so we can't make them visible if we add, for example, an assertion here or here. So what we can do is write some wrapper around this continuation, put this wrapper above the barrier, and add the assertion just right there. So let's do it. So this function, only calls out with the result we gave, and we have the assertions that act as a post condition before getting out properly. And this is the final version of Fibonacci, which on which comma can compute some VCs. This is provable, and we will have exactly the same proof obligations that we would have in Wave 3 or Dafny, for example. But as I said, the hide keyword can be moved in the code, so we can, for example, push it down one level, so we can make visible the first if statement, and let's see what happened in this case. So we are allowed to do this, and now the caller of the Fibonacci function will see the precondition assert n is non-negative, and then it will see that if n is negative, then we fail, but the precondition of fail is false, so the first assertion is redundant with the test that the caller will see. So it is not required to have this precondition assert n non-negative because it is implied by the first test. So we can remove the first assertion. Now we can try to push down the barrier one level more. So let's do it. And it will act as inlining the other base case in the caller of Fibonacci. And now if we take a simple client of this function, for example, computing Fibonacci of 42 and then asserting that it is greater than 100 million, then the contract of this call will be to prove everything above the hide construct, where n is equal to 42 and out is equal to this continuation. So we can write the things that we'll have to prove in this context. So this call sees everything that is in yellow, and we have this proof obligation to ensure the safety of this call, which is what we want to have. So the first test, if 42 is less than 0, then we have to prove false, etc. And now, if we want to prove the function Fibonacci itself, we will have to assume everything that is in yellow and prove everything that is below the height construct. So we'll have to prove this formula, which is not so hard to understand because, in fact, the implementation of Fibonacci is only 2 calls, like the client I just presented, of Fibonacci. So we have the same conjunction here and here, where 42 is firstly replaced by n-2 and then replaced by n-1. And now I can give you some intuition on how the VC generator works. So we have something that we call a modal verification condition generator, which, depending on the context, will not compute the same proof obligation. So we can call C and D the operators. So C is the mode to generate the verification condition at call sites, so when we want to prove assertion until we meet the barrier, and D is the opposite. So when we are in the C mode, when we meet an assertion, we have to prove it and we go down, and then when we will meet a barrier, we will stop. And the D mode is the opposite. We assume the assertion until we meet the barrier, and then we can switch mode and go to the C mode in order to start proving things after the barrier. If you want to go further, you can have a look at the paper I submitted to this workshop to have more examples on how it is useful to have this explicit flexible barrier. And if you want to have more mathematical details, you can read the paper we submitted last year at ESOP. And before concluding, as I said in the third slide, comma is already used by Creusot, the Rust, one of Rust deductive verifier, and it uses the feature of the flexible barrier in a very interesting way, because with closures in Rust you are allowed to prove some, for example, this program where you have a variable and then you take some closures and you apply the closures here to the variable, but you have to write some contracts with precondition and postcondition to every closures whenever you want to know something about the variable after the computation, which in such cases is really not satisfying because the contract is almost 4 times the length of the code of the closure. So I said that the barrier can be moved in the body of the function, but it can also be removed at all, completely removed, when the function is not recursive. So in this case, if we remove completely the barrier, then we can not write the contract at all, and it will be kind of inferred and passed to the map function to have what I mean here is that we don't have to write the contract, but what we will prove is exactly the same on the left side and the right side. And so to conclude, I presented a comma intermediate verification language that features an explicit abstraction barrier and which is used by Creusot. Thank you.
Any questions?
So I didn't get what you needed to
place the hide call keyword on the out call in the example to put it back here. Yeah.
Yes. So the hide keyword so it is a barrier, and it must be placed whenever we want to prove what is below and to admit what is above. As I said just here, when we put an assertion and then a hide, it acts as a precondition.
Mm-hmm.
And what we want to prove here, so if for the color of Fibonacci, what we want to give him as information is that just before going to hide, we have this assertion in the context. If we remove the assertion here, then the caller will have to prove, sorry, not to prove, but to admit everything that is here in the call of out.
Okay.
Yeah, I mean, I was thinking the same because it seems to me like strange that you have to this hide. So actually, you open the barrier, but isn't there a way like at the end to like somehow like closing the barrier in the sense that really so that it's like from a user point of view, it's more clear that okay, I have to put something at the output or like to control. I mean, but this is just like I don't know how. Second question I was going to ask is this like continuation style essentially?
Hello? Hello? 1, 2?
Yep.
Okay. Okay. Hi, I'm Alex. Today I'm going to talk about tunable automation. This is how Varus manages proof context, and we also will get in a little bit of slicing to somewhat quantify automation. So short introduction to Varus. Varus is an auto-active program verifier for Rust programs. Lots of system and security projects use Varus now. You can see them from this on this link. It's used by Amazon to verify some production code. I think this is the one I can mention. And it has relatively faster verification time compared to tools like Dafny. Because one, it leverages the Rust type system. For heap reasoning, we don't do implicit dynamic frames. It also has a more conservative SMT encoding, which I'll get into later. So just to get you familiar with the various syntax, we have spec functions and proof functions, which are ghost functions, what would be arrays and compile time. Spec functions are just like total math functions. It's like Dafny functions. For proof functions, it's like Dafny lemmas, so you can write pre and post conditions and prove things about your spec functions. And we also have executable functions, which are not arrays at compile time, and you can write pre and post conditions that will be checked by the SMT solver, and this will get compiled to an executable. So quantification. It is the primary source of automation for these auto-active theorem provers. It's also the primary source of incompleteness when the solver says unknown. In auto-active theorem provers, we often use user-level triggers. Dafny hides it pretty well, but to guide quantifier instantiation. And here's a short example on how the triggers works. So here I have a spec function is even, saying that umod2 will be 0. I have a lemma saying that my sequence is greater than 5, and every element in the sequence is an even number. And here, however, if I said I want to say the fourth element in the sequence, mods2 equals 0, this fails. This is because I put the trigger here, and the trigger is on the expression, the compound expression of the function composition of is even with a field access. However, I don't have a field. I don't have the call to is even here. So this kind of expression will only be instantiated for ground terms like is even and with a call to the field access. So one way to fix this is to manually put the ground term in. So you can assert that the fourth element is even, and this automatically instantiates this for all with the desired ground term. So another way is to have a freer trigger. We can push the trigger in and put it on the field access so that any field access will instantiate this for all, just like this. So another kind of context for y'all is there, like the Ada core talk, there's an implicit context for these in these auto-active theorem provers. So here's an example that I have two sequences, one that has length greater than 10, one has length greater than 20. If you append them together, I want to say their length is greater than 30. This implicitly uses this axiom that reasons between appending sequences and how their lengths, mostly because these are undeterminate functions. And I'll get into this broadcast thing later. So Varus has this conservative design for verification performance, which normally leads to more manual proofs. There's no preconditions for spec functions because you want to encode them as total math functions. This is a choice also done in Boogie. There's a limited prelude. In Dafny, there are actually more axioms than you needed. There are some axioms that you can just prove directly with a smaller set of axioms. So in Varus, there's a smaller set of axioms, and we prove a bunch of the axioms in lemmas. The axioms in Dafny. There's no nonlinear reasoning by default, and there's a more restrictive automatic trigger selection, which I'll also get into later. So kind of the spectrum of this project is to see how we can increase automation in Varus by pushing it closer to Dafny, and we explore two axes. One is more implicit context, or have freer triggers. So to manage proof context on user level, we introduced this mechanism called broadcast. And these broadcasted lemmas can be imported at any level right after the Varus macro in modules and proof functions and local proof blocks guided by an insert by and in the calculational proofs. So here's an example. I have a sequence of integers A, I push an element 3 to it, and I want to say that the sequence B contains this element that I just pushed in. This fails to verify automatically because Varus is unable to infer this lemma, saying that if I push and then I ask to contain, whether that element is the same one I just pushed or the sequence contains that element originally. But you can write a manual proof like by some sort of induction. And what you can do is you can mark this proof as a broadcast proof. And this will be semantically equivalent to pushing all of the input parameters to be for all guided, like an axiom. And this is all done manually in Dafny, Verifast, and Y3. They're either called auto-lemmas or lemma functions. And this is also the reason. So since all of the input parameters will be universally quantified, you also need to provide a trigger annotation for it. So once marked at broadcast, then you can import this broadcasted proof into your function by this broadcast use thing. And now the thing automatically verifies because of the increased context, and you know which axiom or which lemma to instantiate. And this is exactly how we restructure the Varus standard library on these collection types. So in the past, we have all of these extra Dafny axioms now proven in Varus, and we throw them into a large group, universally quantified all of them, and throw them into this huge lemma. And with this broadcast proofs, we can also group them together in chunks, and we can import at bulk for all of these lemmas. And this is exactly how we organize our code base. And so you may not want to find this lemma C contains lemma. What you can also do is just import this huge bulk. But then you might be concerned because now you're increasing the proof context by a lot. So if you're worried about verification performance, we also read the unstacked core from the SMT solver, and this will tell you that for this thing to verify, you're using this group, and in particular, you're using this lemma. So what you can do is, OK, now let's just shrink the context guided by this unstacked core. And with this mechanism, we also have a nice way to modularize proof libraries, especially on user-defined abstractions. So in one of the projects, we have a trait of keys. And for this trait of keys, for any instance of this trait that needs to prove the obligations, most likely like your key works like you have a partial order on the keys. And then you can mark some of the properties on this key, like the partial orderness, as a broadcast proof, and you can group them together so that you can have a user-level axiom set about user-defined abstractions. And this is also done, we rewrite one of the projects to use this abstraction, which works out pretty nicely. So now with this background, we can talk about how we explore the automation trade-off. So I just talked about there are a bunch of Dafny axioms that we manually proven in Varus. These are grouped as like these group seek properties and these collection data type stuff. So one way we can just broadcast all of them in some existing projects and see how impactful it is. So, and there are two questions, right? One, how much does it improve automation, and what do I mean by this? And the second one is if this blows up your verification project by like a long verification time or even proof fails. So we studied 4 projects, all written in Varus. I'm not going to go into them. You just need to know they exist. And to quantify automation, we need to introduce some sort of metric. And here we just looked at the number of asserts. However, most of these projects doesn't start with the minimum number of asserts because you might want to guess what the proof state is. Some might be useful for documentation purposes. So what we do is we have a syntactic tool to minimize the number of asserts in a project. This is, of course, not the real minimum. We are not doing a combinatorial thing. We're just doing a linear scan, looked at assert, remove it, see if the project still verifies. If it still verifies, then keep it removed. And another limitation is we're only targeting assertion. So we're not targeting lemma calls for complicacies. So as I said, we're trying to broadcast a bunch of stuff. So what we can do is we can minimize the projects in one run, and we can broadcast all of these stuff and then minimize them again and compare their difference to see how impactful these group properties are. So here you can see, actually one interesting observation is that more than half of the asserts in these projects are not useful for the SMT solver to find the proof, which is interesting. And for the broadcast, around 2 to 8% of manual assertions can be removed. And for the verification time, you can see there's a large vertical line here, meaning that most of the functions verifies about the same time as before. Only like 1.8% of functions verify them more than 2 times of their original verification time. And this is kind of exactly what we want with this user level control of automation, so that for these problematic functions, you don't need to broadcast all of these extra facts to speed up verification time. And next, I want to talk a little bit about triggers. So in Varus, the automatic trigger selection only selects one trigger in multiple possible triggering candidates. So for this universally quantified expression, you have F, G, and H, which are all like Boolean predicates. And there are lots of valid trigger candidates. For valid trigger candidates, it only needs to cover all of the X and Y so that you know how to instantiate them. However, some are useless candidates because, for example, this one will always be triggered by just having the trigger on H. So normally you take the minimum cover, which is this all trigger expression. So what we can do is see if we can move from the default or the user-provided manual triggers to this all trigger thing and see how impactful this is. So one thing we can look at is, well, we have this group seek properties, whether we can free the triggers in these more like Dafny axioms. And the answer is no. Like you cannot free these triggers without causing an explosion in the trigger instantiation. So this S1 and S2 are just like the the X and Y's in the previous example. So the other valid trigger groups will be put a trigger on these 2 expressions. However, these will match on any 2 calls to length of a sequence, causing explosion. So another place to have freer triggers is on user-introduced universal quantification in those lemmas. And this is what we did in one of the smaller projects that are in KV. We replaced all of the trigger annotations, if possible, to all triggers. There's one proof that broke, and we omitted it because of context manipulation. And we run the same minimization thing on it. And you can see that this actually is more impactful than like increasing the ambient facts. We're broadcasting a bunch of stuff. And for the verification time, there's a slight decrease, but it also works out somewhat fine. But it's less clear to us. So it has a non-trivial impact, but it's less clear to us how do you manipulate these stuff automatically. And one future direction might be to annotate multiple trigger groups. If you want a more automatic version, you can try to be freer with triggers. And that's all. Thank you for listening, and there's a preprint available online on arXiv.
Any questions?
So about the use of these broadcast lemmas, or like use or not use. I mean, as a user who is not aware that I should use these lemmas, or like how do I approach a program when I want to prove some things about sequences? And in particular, for example, Varus errors. Sometimes like I think there's been some improvement, but it's not so clear. Like maybe it should be like for the user guidance. Okay, you can find this lemma and try to use this lemma. Like, and also in terms of minimization. Maybe like, do I really need to actually import the lemma when you said that you can actually automatically perform this, like import the whole block, then reduce to the actually useful lemma?
So I think one of the things is like we want to see how many conservative choices in Varus are valid. The reason, and like by importing these lemmas by default, yes, you can kind of import all of these properties lemmas by default and try to see how it goes. It's just not done in default because initially we want faster verification time. And for the other question, So there's currently a PR called Sledgehammer. The name is probably going to be changed. It does some sort of semantic search on what kind of stuff you can be broadcasted. I think you can kind of go pretty wild in this direction. Like technically every lemma that you wrote can be a broadcasted lemma. And you can do some sort of semantic search and see if it automatically verifies, but this is all in the future. Right? Yeah.
And actually also for the triggers, because it's just like somehow the same problem, like because I was using like some, just not using really, but like playing with Dafny with some, and then using Verus, and then suddenly like maybe in Dafny there are also trigger issues, but like in Verus suddenly like these trigger issues appear, and usually like there is like this default like some warning.
Tell you about Velvet. I will have to sit for this talk, not just because I made it all the way from Singapore, but because that's a demo-based talk, and actually you can get all this, all the code I will be showing you on these links. But without further ado, let's check out the code. You can see the lin file, which oh no. Okay. Yeah, let me try to. All right. Yeah, somehow I cannot mirror the screen. But Control F1. No, nothing happened. Okay, let me just. Let's try this way. It's gonna be fun.
You can take 2 seconds to duplicate the screen, otherwise it will be hard.
Yeah. I mean, honestly, I'm not even sure what file is that. Yep. Okay, I guess I will have to sit like this. All right, this is the lin file, which might be a bit surprising because we are on the Dafny workshop. So aren't we supposed to talk about Dafny or?
The phone.
Yes. Like this is fine. Okay. So we are supposed to talk about Dafny, or like at least autoactive verifiers, and well, we implemented one in lin, and now I will try to convince you that that was a good idea. Well, you can see the very first example of the program verified in Velvet. This is the square root. It's an imperative-looking style code with some annotations. You can also run this program, of course. Well, the square root of 9 is 3, so it seems correct. It's also correct on other numbers. I checked last time. So yeah, and now we want to verify it in Lean, right? So how do we kind of do this kind of Dafny-like verification in Lean? For this, we have a special command, proof correct, and the tactic, which will generate us a bunch of verification conditions as pure Lean goals, which are equivalent to the soundness statement of this program. You can see there are a few of them, and well, now you can just go on and prove them using Lean tactics or maybe with some automation. So one way to do automated proofs is basically just that's a parameter in Velvet. You can say, well, try to prove them with CVC5. And you can see that it managed to prove everything with CVC5 using the Lean Auto backend, which connects Lean goals to SMT. Yep, and well, so far nothing really surprising, but remember that in the title of the talk, we had this cryptic phrase multi-modal. What does it mean? It means multiple things, but for example, Velvet has multiple semantics modes for the verification. For example, this loop. We have a while loop. You might be wondering if we prove the total correctness or partial correctness. Do we want to ensure that this loop terminates? And that's exactly what is the parameter in while. So you can set it up yourself. And one way to, so the way to set it up is basically using Lean options. The option that is responsible for the termination is this one, and you can make it either partial total. I will show you the total example a bit later. Another thing that you can control is the semantics of a non-deterministic choice. Well, let me show you the program that uses this non-deterministic choice first. So this is a very simple program which converts the Boolean predicate on a finite type to an array. Well, so you see one thing is that the predicate is mutable because we will be chopping elements from it one by one and basically pushing them into the array. So the specification is here. We have to, because the variable is mutable, we have to refer to its initial value, and the convention in Velvet is just you put the old suffix. Well, now in the loop, you basically pick the element non-deterministically. This is this set phase from Dafny, which is called Hilbert choice operator, basically non-deterministic choice. And now you can run this program. When you run it, this non-deterministic choice means basically random sampling. But when you verify it, because we just set it to demonic, that means that the semantics of this non-deterministic choice would be just for all quantification. So we will have to prove our specification basically accounting for all possible choices that could have been made. Also, it also makes sense in some other applications to use the existential quantifier semantics for non-deterministic choice. This is very useful for symbolic bug finding, but I won't be showing this example here. You can find it in the paper. Yep. So now let's go and see a little bit more complicated example, which is the insertion sort. This is the code in Dafny, and this is how it looks in Velvet. More or less the same code and more or less the same annotations. But now let's get back to multimodal part. In Velvet, we can not only just symbolically verify the code, but we also can try to find shallow bugs using property-based testing. Yep, and let me show the example. So let's mess up our specification a bit and make it too strong. Yeah, a bit too strong. So now there are a bunch of comments, and the property-based tester, this is a simple code for it, will immediately give us the input for which the post condition is violated. You see that this input contains at least 2 repetitions of -8. So yeah, that's the way how you can use property-based testing. And also, of course, our verifier will say, oh, actually, I cannot prove this assertion. And the coolest part is that you can go on here and see the whole context, which is basically with all the facts that are true when you want to prove this assertion. And you can debug it here right now. Okay, let's now do something else. Oh no, okay, whatever. This should work too. So we will make our specification sound again. And here. And now we'll mess up with the code a little bit. So let's remove this line which is responsible for the progress. Without this line, our program will just loop forever. And the question to the audience, do you think it will still verify? Yeah, it is partial, and yes, that's why it will verify. So it does verify here, no goals. Yeah, that's because it's partial. So as I promised, this is a parameter, so we can change it and make it total by uncommenting this line. Yep, and now as soon as we uncomment this line, you can see that Velvet now tells us, oh, actually you need decreasing annotations if you want to verify it in the total correctness semantics. So let's just add those decreasing annotations right away. Luckily, I have them here. And now it will think for a second, or maybe 2 seconds, and verify it again, because I need to comment out the partial one. All right. So now it will think for a second and finally give us what it was supposed to give in the very beginning. Basically, it will say, oh, I cannot verify this decreasing annotation. And now you can basically look at the context and try to debug it. But luckily, we know what is causing the issue, this line, so we can comment it in back. And then the program will be verified. This is actually not the only way how one can play with different semantics in Velvet. One more way is the benefit of building autoactive prover on top of the foundational proof assistant, because you can now take the proofs and manipulate them as first order citizen and combine them to have something stronger. For example, for the same insertion sort, you can first prove it under the, you can first prove determination. So here you can see you have the total semantics, right? And you only prove the post condition, which is just true. So you only have annotations related to the verification, to the termination. So that's one proof. And then you can also separately prove the partial correctness with the desired specification. So something that we have seen just now. And using these two proofs, you can rewrite your programs without any annotations with the spec that you're interested in and prove it in the total correctness without even calling any automation. You just basically combine the two proofs that you had before and use this lemma, which says that, well, you can build the total correctness out of termination and partial correctness. So that was one way how we benefit from building attractive provers on top of Lean in this case. And another way, which you might be more interested in, is using interactive mode when in Lean tactics when automation fails. So the example here is the function which we implement ourselves. This is the function which computes if some number is prime or not. So it is fairly simple implementation. And then if you will try to run it, so here I disable automation for a second, so you can see that it generates 15 goals. And now if I remove this line to bring automation back, it will solve everything except one goal. So now we can just go ahead and try to prove it manually. But hey, aren't we in 2K26? I heard that there are so many, like bazillions of different LLMs which are incredibly good in proving pure Lean goals. Can we just try one of them and see what will happen? So we have a simple script which basically hoists the goals that we have in the proof correct statement as the theorems. And then you can put sorry and use the LLM of choice, Claude Code, Aristotle, what have you, And here, it actually produced a proof. You see the proof is quite involved. One interesting fact is that it uses ASOP cut, which is the ASOP tactic with some category theory tuning. Apparently, this is useful, I guess, in this proof. But the point is that this is an involved proof. So let's see what it actually tries to prove. It proves that basically your the number is prime is not prime is prime if and only if it has no dividers between 2 and the square root of this number. So this is not exactly a trivial fact. But you can still automate it fully with Velvet and AI, which means that Velvet kind of bridges the gap between all this success in AI for math and what we care about as POPL community, software foundation, software verification.
Question. So how did the AI work though? I mean, is it that file?
Oh yeah, I don't show how AI works, but basically you put sorry here, and then you say, oh, either you say, okay, can you please fill this sorry, or you use some scripts in case if you, for example, do Aristotle. So somehow you.
So you let Claude edit that file?
Yes, yeah, exactly. But that's not the most impressive examples. We have another program which actually is not written by us. This is from some other project. This is a memory allocator. So this is a function which does some graphs labeling. It doesn't really matter. It's just not a entirely trivial function. Let's see what happens if we try to verify it with LoomSolve. Well, okay, yeah. It leaves us 7 goals to prove manually. And well, we run our script again. We hoist them and ask AI to prove it. Well, it managed to. It actually takes quite a bit of time. Let me explain why. There is one beast goal. It has a. I cannot, I guess, now describe what does it mean exactly, but it's called goal 6. Yep. And yep. So the proof is quite involved, but that's not. But it actually gets cooler. To prove this goal, AI had to come up with the whole small small theory of facts about acyclic path, and it goes on and on and on. All these things are AI generated. Yeah, this help us theorem is about acyclic path. That means that now using kind of Velvet plus AI, you can automate the tasks which require developing theories, and this is, I think, quite cool. Yeah, that was it with the demo. I will see if I can. Oh no. Oh yes. Yeah. Okay, it works. Yeah. Just a couple of seconds. If you're interested, some couple of forward pointers. If you're interested in the foundations of Velvet itself as a tool, you can visit my talk on Friday. The tool is called Loom. This is foundations for all these kind of provers. Then, if you're interested in other things that we built on top of Loom, so Velvet-like verifiers, you can stay for a bit. George will give a talk on Veil. That's the after lunch. That's the verifier for distributed protocols, and also George and Chuan, they will give tutorials on this tool. I really suggest you visiting it because this is also mind-blowing. Yep, that's it. That was Velvet. Thank you very much for your attention.
Okay. First of all, that's really, really cool. And second, my question is, does your AI also generate the invariants and ensures and for alls? I mean, ensures and for alls. Ensures and requires, sorry, I guess you don't want to generate them because that's what you want to prove. But the invariants, do you generate them at all, or?
Yes, we have some experiments that we try, and it actually, yeah, I guess stay tuned. We will have some work about it. But yes, we tried, and it actually works. But one thing that really helps when it has some suggestions for like invariants, right? It really helps that we can execute our code and basically property-based test invariants as well. So this will kind of help it to have the feedback loop, and that's quite important here.
Thank you for the talk. So I was curious about how you, or do you handle recursive functions at all?
Oh yeah, that's a great question. We right now redesigning a bit the framework to have the better support for basically arbitrary recursive functions with the kind of also total partial correctness proof. But at this point, with the recursion, we only handle the well-founded recursion. So basically, the recursion where lean can make sure that the program terminates. And then you will have to do basically this standard lean extrinsic proofs that function terminates. Yeah.
It's something like the 91 function, right, where you have the proof of the. There you go, the classic.
That's not the first time we got this question, and that's exactly why we are redesigning it to support arbitrary recursion. But yeah, it's possible. It's really technical reasons why it doesn't work exactly there, but it should, yeah.
Okay, cool. Yeah, I'm very bought into this stuff, so this is very cool. The title of the talk said effectful programs. So I see mutability here, but I'm just wondering if you've considered other program effects.
Yeah, that's a great question. So the other program effects which we consider in Velvet are non-determinism and non-termination. This is for Velvet. We're thinking of adding exceptions, but so basically we have this library of kind of effects and the ways to deal with them, which is called Loom. So please visit my talk on Friday, where I will tell much more about that. But another thing is in Veil, that's another framework for these Veil protocols. We support much more effects, including also exceptions, state, only read-only state, and stuff like that. So yeah, different kind of effects are supported. We have this special library for that.
Lunch. Let's thank the speaker again.
You have 1 hour and a half for lunch. Use it, but be sure to come back on time here because we will start on time. Thanks for the speaker as well. Thank you.
to share a bit about what we've been doing for the past 20 months or so. So Vova, Chuan, and myself have been building what I really believe is going to prove to be the future of auto-active verification. And I'm very excited to share the vision of what we're doing with you and share some of the lessons we've learned along the way. And my hope is that this talk gets you excited, it gets you to try Lean out, and maybe, who knows, gets you to build an auto-active verifier in Lean. That's what we've been doing for the past couple of years now. And we've been building this tool called Veil. And I assume most of you don't know what Veil is and haven't seen it before, so I will introduce it. And the keyword soup is that Veil is a multi-model foundational verifier for distributed protocols. This is not a very technical talk. So if you want the technical details, my colleague Vova will give a talk at POPL on Friday morning. So do attend that to get all the gory, cool details. This talk, however, is a bit higher level. And when I think about Veil, well, Veil for me is first and foremost a tool I built out of immense frustration at the state of existing tooling for verifying distributed protocols. And you can kind of plot the existing tools or existing approaches for this problem on this kind of plot, where the x-axis is the amount of time or effort you should invest to use these tools, and the y-axis is the benefit you can get by applying them in terms of, say, number of bugs you can find or classes of properties you can establish, and so on. So the easiest and cheapest approaches, concrete state model checking. And when it comes to distributed protocols, TLA Plus really is the king here. It's a very mature tool. It takes an expert maybe a couple of days to model a protocol in TLA Plus and model check it with TLC. It's very widely used in the industry, and so on. The problem with it is, even though in principle you can do proofs with it, in practice most people don't, because the tooling is quite bad for that. If you want to not just test your specification, but actually verify it, the tool to use for distributed protocols is this tool called Ivy. And this does SMT-based verification. And crucially, this is decidable SMT-based verification. So Ivy forces you to write your specification in a decidable fragment of first-order logic, which is very often possible for distributed protocols, but requires quite a bit of expertise to do. And once you do that, it lets you automatically prove your protocol correct, not just test it. And the fact that this is decidable actually gives you two major benefits. One is it makes the verification very consistent and stable. So you don't see the instability issues that auto-active verifiers usually have. And secondly, and just as importantly, and perhaps even more importantly, is it gives you a lot of tool support when verification fails. It gives you very concrete, clear counterexamples. And I'll show you an example of that a bit later when I give a demo. The alternative to this would be to use a tool like Dafny, which does general SMT-based verification. And people have been using these kinds of tools for distributed protocol verification. But the tools are more powerful, of course. But the power comes with cost. The cost is instability, and you don't get as much support when verification fails, which is the usual case when you're verifying a protocol. And finally, you have interactive theorem provers, and you can use interactive theorem provers to verify distributed protocols. These are very powerful tools. You can state any property you want. You can prove any property you want. You're just going to spend a lot of time doing it. So what people do in practice in industry is they kind of use the approaches on the left. So they use TLA a lot. And sometimes they might translate their specification to Ivy and do some proofs with Ivy, automated proofs with Ivy, use Ivy to come up with an inductive invariant. And you see there's this trade-off between expressiveness and automation. I don't like trade-offs very much. I want to do everything. So part of the trade-off, of course, is fundamental. You can't get around undecidability. But a large part of the trade-off is actually due to bad tooling. So what I want to do is I want to use all of these approaches in a single tool. You know, what do you have to do now? What's the state of the art? Well, the state of the art is you kind of start with model checking and test your specification. And once you want to do more, well, you have one of two options. You either use a combination of tools, and that has issues around having to translate your specification and potentially introducing bugs when you translate to a different tool, or you add an interactive escape hatch to your automated tool, as we've seen in the morning session. I mean, it makes sense, but I think this is the wrong approach. And I've seen it happen so many times. I haven't tried the Dafny tool, so I don't want to criticize prematurely. Maybe this is the tool that breaks this pattern. But all the other tools that add interactive escape hatches to automated verifiers are really, really bad in terms of user experience. I made this remark to my advisor, Ilya, a couple of years ago after seeing this happen again with another verifier, no Dafny. And it seems like almost like a law of nature at this point, right? So I will postulate it as a law. Every verifier expands until it contains an ad hoc, bug-ridden, unusable implementation of half of an interactive theorem prover. Those verifiers which cannot so expand are replaced by ones which can. And I mean, it's a joke, right? It's kind of a joke, but it's also, I think, entirely true. And my work, if people are to know me for anything, I want people to know me for breaking this pattern. We don't have to live like this. There is a better option. It's called Veil, and it solved these issues. And the way we did it is really quite simple in principle. We just built the whole verifier in Lean. So rather than bolting on an interactive theorem prover to our auto-active verifier, we take the world's best interactive theorem prover and build a great auto-active verifier in it. So the proof is in the pudding. So let me show you what it looks like. Very quickly. You don't see my screen. Let me mirror. All right. So just as this morning, this is a Lean file. All you need to do to bigger. OK. All right. This is a Lean file. All you need to do to use Veil in a Lean file, you import Veil, and that makes available to you a DSL and a bunch of tools. So I don't have a lot of time. I'll mostly flash this. But the DSL is imperative language that lets you specify transition systems. So you specify the initial state, you specify the actions or transitions of the system, and then you specify the properties this system must satisfy. And then what does Veil let you do? Well, it lets you do everything you saw on that slide. It lets you do concrete state model checking. So let me introduce a bug in this protocol so we see kind of what this looks like. So that ran a concrete state model checking. And this is all Lean in VS Code. We didn't write any extensions. This is the regular Lean extension. Shows you a counterexample to the property we just broke in this protocol. Let me fix the protocol. And that was explicit state model checking. We can also do symbolic model checking in Veil. So here, let me make this bigger. We are doing a satisfiability query for a trace. So it's saying, well, there is a way of executing this protocol with any parameters, any number of nodes, such that you can take 3 actions, and at the end there's a leader. So we want to check whether this protocol is vacuous, right? And the solver tells us, well, yes, there is. Here's the trace. We can also do bounded symbolic model checking. Here we're saying we can take 5 actions, and then there's no way, basically, to elect 2 leaders. So this is a leader election protocol. This is a safety property. It says, well, yeah, no counterexample found. If we break the protocol, that will take a bit. This complains, and this will complain. And we see, a trace, a symbolic trace in this case, that shows 2 leaders being elected. OK, finally, and this is what I promised with Ivy-like verification, what does being in a decidable fragment of history logic buy you? Well, it buys you inductive invariance. So let me fix the protocol again. And when you're verifying a protocol, the hardest part is coming up with the inductive invariant. So say we are in the process of coming up with an inductive invariant. What being in a decidable fragment of first-order logic gives us is very nice counterexamples to induction. So here, the verifier is telling us, well, look, your protocol is not inductive. Your invariant is not inductive. Here's a concrete counterexample. So if you start in this pre-state that satisfies all the invariant clauses you've told me about, and you take this action, you get into a post-state that violates the invariant clause. So what this means is you must strengthen your inductive invariant with an extra clause to eliminate this pre-state. Okay, that's all I have time for in terms of the demo. Let me go back to the slides. If that piqued your interest and you want to learn more, we're giving a tutorial tomorrow afternoon. I'd love to see you there. Okay, so Veil is not fully there yet, but we want to have all of these approaches at your disposal in a single tool built in Lean. Okay, so what have we learned besides the fact that you should build auto-active verifiers in Lean? Well, it's not all milk and honey in Lean land. So this was a sales pitch so far. The reality is it is very good. Like Lean is very good. It's a great tool for building verifiers. But you are going to face some hardship. So we learned a few things developing Veil. Some are quite obvious. So for instance, good software engineering practices are still things you should do when you build verifiers in Lean. So obvious stuff like testing. You need a lot of tests. It's hard to write correct programs. It's a lot harder to write correct meta programs. So you really need a lot of tests. And then things like modularizing your code and so on. So this is quite generic. I'm not going to dwell on this. More specifically, though, meta programming really is a two-edged sword. Meta programming has a steep learning curve. It took me about 3 months where I felt I had no idea what was going on, and then it clicked, and I felt like on top of the world. I can do everything. Everything is a meta program. I can implement anything. You can do anything you want. The fact that you can doesn't mean it's necessarily a good idea. So you can get yourself into really some unmaintainable messes with meta programs. Spaghetti code is bad. Spaghetti meta code, forget about it. Okay, I'm going to expand on this on the next slide. The next 2 points are a bit technical, so if you're interested in the details, I'm going to be vague about them. If you're interested in the details, do read the manuscript we've put up. It's linked in the program. So it's nice to be shallowly embedded in Lean, as Velvet and Veil are, but you shouldn't be too shallowly embedded in Lean. So what I mean by this is if Lean constructs are interfering with your representations in your verifier, you're doing something wrong. You should control all your inputs to your verifier. Lean should be kind of a backend that you put definitions into, not, again, read a paper for details. It's a technical point. Slightly more general, but also a technical point, generality comes at the cost of complexity. So I've shown you a demo of Veil. You have all these tools at your disposal quite seamlessly in the front end. There's a lot of complexity on the back end to make that happen. And you, as a maintainer of a verifier, have to pay the cost of maintaining that and keeping it performant. And this is my last lesson. Performance is a huge issue. Like by far the biggest issue we have building auto-active verifiers in Lean is they are slow. I'll get back to this. Let me illustrate these 2 points a bit more at length. So what I'm showing here is the first version of Veil and the output of the check invariance command. So this is kind of what what you saw as a widget. And let's think about what this command kind of does. If you think about it, this is like 80% of the verifier. So let me go through the functionality of this command. So this goes through the Lean environment. It identifies every action you've declared. It identifies every property you've declared. It builds a Lean expression that corresponds to every verification condition that this specification kind of incurs, it translates that expression from higher order logic to first order logic, sends it to an SMT solver, gets back the result from the SMT solver, prints the result, either green check mark or red cross with a counterexample, and then, because we're working in a foundational setting, for the theorems that succeeded, gets the proof from the SMT solver, CVC5, and reconstructs the proof in the lean environment. So you don't have to trust the external solver. That's a lot of things to stuff in a single meta program. And I mean, we kind of did stuff all of that thing in the original version of Veil in there, and it was a disaster. Like, it was completely unmaintainable. So for the second version of Veil, which we're about to release soon and which you've seen, things look a lot different. From the user's perspective, okay, sure, this is a nicer widget with incremental progress, but the backend is completely different. And the key insight, and I think this generalizes, is we found out that this model view controller architecture, which is very common in software engineering, makes a lot of sense for building verifiers. So the core of Veil 2.0 is this data structure called a VC manager. And basically the way this works, and I'm not going to go into details. If you're interested, do read my PhD dissertation when it comes out later this year. But the idea is the actions, the elaborators for the actions and the properties in your system put in obligations into this VC manager. The VC manager has logic for discharging these with external solvers, with, say, interactive tactics, and so on. And then checking variance is just a view. It just reads from the state of the VC manager, which does all of this asynchronously and displays a widget. Details in the paper. Finally, performance is a huge issue. So this is data that's almost 1 year old at this point, so don't look at the details. The gist of it is we're about 10 times lower than the closest comparable tool, IV. The largest chunk of it, so basically the blue and light blue chunks are overhead we incur because we're in higher order logic and we need to translate to first order logic. The green part is the solver time, right? So for very large specification, the solver time dominates, but we're still a lot slower than tools built the traditional way. That's the main challenge. We do hope that with more engineering, we can reduce the overhead to maybe 2, 3x. We're always going to be slower if we start with higher order logic and have to translate it to first order logic compared to a tool that just produces first order logic directly. But, well, you know, you take the good with the bad. That's all I have. Thank you very much. You can try Veil online on this online environment at try.veil.dev. So try it out on your laptop. Thank you. Okay. Can disconnect for the next play. Yep.
Sets up.
Thank you for an interesting talk. Could you comment on what is the link between Veil and Velvet?
Yes, they use the same semantic foundation. So basically, the semantics of Velvet and Veil are exactly the same, right? It's this framework called Loom, as is very much inspired by Dijkstra monads. You can more or less interoperate between the two. So they are, in some sense, the same core logical foundation with different instantiations.
Okay, my name is Wieger Wesselink. I'm going to talk about an application of Dafny to Minimax search. It's joint work with Kees Huizing, who's also present here, and Huub van de Wetering. I'm first going to explain the problem domain, the foundations of game tree search, and specifically about the verification challenge. And afterwards, I'll talk a bit about our experiences with Dafny. The setting is we're looking at two-player games where zero-sum games, so the gain for one player is a loss for the other, alternating moves, and we really look at trees, so there cannot be cycles in the game. And we can model that using game trees. So we have just the nodes are game states and the arrows are moves. And then we have a playout is just a tree, and in the leaves we know the results, these are just numbers. And then we assume there's optimal play for both players. One player tries to minimize the score, the gray nodes, and the white nodes is a maximizer. And then you can just bottom up compute the game tree value for the root by just depending on the minimizing or maximizing player, taking the minimum or the maximum of the children. A well-known classic algorithm to compute that value is a recursive algorithm called Minimax. It just goes top-down through the tree and evaluates the children and then recursively computes that result. Negamax is just a shortened version of Minimax, and that's one is used in practice a lot. That's the one we will focus on. And we will add 3 practical features to it to make it more interesting. And these are alpha-beta pruning, depth-limited search, and the usage of transposition tables. This is used in practice a lot. There's a lot of subtleties with these algorithms. They are not fully understood, and we try to verify them using Dafny. So I'll explain these 3 features first. Alpha-beta pruning is a way to increase efficiency. It's based on we expect the value to be in a certain interval alpha-beta, and inside that alpha-beta interval we want to have exact results, so a true Negamax result. If the result is to the lower than alpha, then we are satisfied with knowing that it's just an upper bound, or on the other hand it can be a lower bound if it's to the right of beta. So we can have 3 different outcomes, an upper bound, an exact value, or a lower bound. And this helps to prune a lot of unnecessary parts of the tree. Second feature we add is depth-limited search. That's just, in practice, these game trees are so huge that you cannot compute all the way to the leaves. So we just stop the search at some depth limits, and then we use that to evaluate the result. That means that we also need values for the internal nodes, not just for the leaf nodes. So usually people use some heuristic to give a value to the internal nodes. And the last feature we will focus on, that's the most important one, is using transposition tables. The idea is that for game states, we do not want to have repeated evaluations. The same game state can occur many times in the same game tree, and you want to reuse those results by caching them in a table. And what people typically store is the value of the search and the depth that was corresponding to that search, but also the kind of the search from the alpha-beta result. Is it a lower bound, an exact value, or an upper bound? Note that the alpha and the beta themselves are not being stored, so it's not a complete result, but that's what people use in practice. And we are going to look at 2 different algorithms with those settings. One is a classic algorithm from Marsland from 1986, and that uses those 3 features. And the other one is the current version on Wikipedia. And they have, I'll first show you, there are 4 differences between those 2 algorithms, but I will only focus on the first one. And let me go back to explain you a bit about the structure of those 2 algorithms. Note that there are 3 different phases when you use a transposition table search. The first phase, the top one, is the table lookup. You're searching a node U, and first you check, is it in a table? And if so, we can use the table result either to return directly or do something with it. The second part is just the Negamax search. You do the Negamax algorithm. And the last part is you get a result from the Negamax algorithm and you use it to update your table, your transposition table. Now, it turns out that there's an important difference in the table lookup. If you look at the Wikipedia version, let's go there first. That is a very conservative approach. We just look at the table, check if the depth is big enough, and then we can use it. And if it's a good result, we just return it and stop. So then we're done. Otherwise, we just do a normal search. But now the Marsland version does something different. It does also do lookup in the table, check the depth. If it's exact, we're done. But if it is an upper bound or a lower bound, Marsland says, no, I'm going to shrink the alpha beta interval. I'm trying to get an exact result, so I'll continue the search with a lower depth. It seems to make sense, but it turns out that this really affects the correctness. The other three differences, turns out they are more or less optional. We can just apply them in both algorithms or not and still prove correctness. What's important to realize is that actually the correctness of these algorithms is undefined. Nobody has ever specified, at least to our knowledge, what correctness means when you use a transposition table. So that is an important part of the verification. People in practice also talk about this a lot, all these differences, but anyway, that's just, it's very subtle and people have all kinds of opinion about what is correct and what not. So that gives also motivation for doing this kind of research. So now the most important part of our work is just, we have tried to define a correctness criterion for transposition table search. First I'll give you an intuition what that means. And our idea was, well, that result is unspecified what it means, but we think there should be some kind of game tree that explains the result, such that a game tree has a negamax value that is equal to the result of the transposition table search. And why do we think that is the case? For that we look at what does a transposition table search look like? Well, it is a depth limited search, so the left picture shows the nodes until that depth limit. Those are being searched normally. But if you have a transposition table hit, it's shown in the second picture with a black dot, then you just have a lookup and you do not explore the results below. So those ones are skipped. But if you think about it, it's a transposition table result, maybe at a higher depth. And there were also nodes contributing to that search. So if we plug those nodes in, we get a picture on the right. These are all the nodes that have contributed to the search, and that can even happen recursively. So that transposition table search here can also have used the transposition table before. So it really becomes that kind of wild structure. But our hope is that this gives us a game tree that explains the result of the algorithm. And to formalize that, we made some criteria for what we call that game tree a witness. And we formulated, say 4 requirements for what a witness is. So we want it to be a subtree of the original tree. It should have the same negamax value. It should also be it should include the full tree until depth D, because we have a search of depth D. And lastly, that's more for soundness, if we have a node in a witness, it should include all the children of the original node or none, but not just a selection, because then you get very weird trees that correspond in no way to minimax. So you have either all children or you just leave them all out. This was our criterion. We applied it to that 2 algorithms that I showed. The Wikipedia version we managed to prove correct using this. It was about 800 lines of code and verified in 4 seconds. But the Marsland version, we did not manage to prove it, and actually we managed to show that it violates our witness criterion, so it does not satisfy it. And for that, Dafny was actually quite helpful, because we almost managed to prove it. There were just 2 configurations where the post condition we were unable to prove it, and this is just one of them, where we have the initial alpha value was moved to the right because of a lower bound hit in the transposition table, and the end result was between those alpha values. That was the difficult problem. And this inspired us to look at this as a possible counterexample. We managed to get a concrete search tree that really showed that that this Marsland algorithm does not satisfy the witness criterion. We have a window of 0, 5, we have this small tree, and we have search depth 2, and we have a table that's already filled with a lower bound at depth 3, so a higher depth. And this was quite a puzzle, but we found it based on those hints from Dafny. Now, why is this a problem? The two problems. One is that the return value is 2, and that really is not a minimax value, because the parent of the node 2 is a gray node, is a minimizing node, and you should expect at the between the depth level that it should always minimize, so return the node 1. But because of that table hit, the window has been shrunk to 3.5, and then 2 is outside the window, and the result, the node 1 will not be visited. So it's a questionable result. But moreover, it also does not, there is no witness game tree that results in the value 2. It does not exist. If you extend this depth level to 3 with the nodes 3 and 4 or not, the result is always 1, 3, or 4, but never 2. That's not there's no witness that results in 2. So really this example shows that the criterion does not hold. We actually managed to extend this example to a search that starts with an empty table. So then it includes the previous example. So this shows that Marsden does not satisfy our criterion, which we thought was quite natural. Okay, so now the last couple of minutes I will briefly explain some experiences with Dafny. Well, the modeling in Dafny was quite concise. We were very pleased with it. We did, it just looks like this. We have bounded integers as a constrained data type. These are just the predicates for describing the witness. Also, we not only need to look at the result value, but also we need to look at the transposition table that should also only contain results for which a witness exists. So we see that here, that in the transposition table should also be required. Yes. Well, here we have the expansion predicate that is part of that witness. We managed to define it without relying on other predicates, so it's really self-contained. That helped a lot. We have been improving all kinds of properties and put them in lemmas, like it should be reflexive, it should be transitive, it should have include the depth-limited part, and all these things that could even be proven automatically using Dafny. A very major issue was the proof stability. The specification contains a lot of quantifiers, and then you typically get symptoms like memory exhaustion, like in 15 seconds your whole memory is taken, you can reboot, and that happened countless times. And also that the verification sometimes doesn't terminate. What did we do to avoid, mitigate that? We avoided inline proofs wherever we could. Always use lemmas instead of inline proofs. Also put lemmas at strategic places, sometimes where you thought it should not be needed, but just do it. I will give you an example soon. Keep the formula small. If you have a large formula, put subparts into predicates. And as a last resort, use opaque predicate to hide the definitions. Here we see an example of these lemma calls. So just in front of at the end of a loop or in front of a break, that's a place where proof obligations hold. We insert a lemma. And actually this happens a lot. If you change the invariance, you need to do it again. I would really like to have a feature that Dafny helps me to generate a stub for such a lemma, because it's a tedious job. You need to do all kinds of calculations to find the exact state at that point where you call the lemma and put them in the requirements. I think it can be automated and it would be quite helpful. Finally, let's skip this. There's also functional programming. Let me wrap up with the conclusions. We introduced that witness-based correctness criterion. We verified the practical algorithm is non-trivial. We did 15 to 20 more of these algorithms. And it really shows that Dafny is a good tool for doing this kind of research. Thank you.
talk. I'm wondering, do you have any assumption on the heuristic that you use when you reach the depth? Is there some correctness assumption about the heuristic that when you haven't yet fully explored the tree, but you have to stop at depth 3 or something?
No, the thing is, if you do depth-limited search, you have no guarantee whatsoever about the result. It can be arbitrarily bad, because it really depends on the quality of those heuristic values, and they can be so bad that every winning position can become a loss, so you can't help that.
In this case, what does the correctness criterion that you introduce help you with? What does it tell you other than can be arbitrary?
No, it gives you at least an intuition for what does that value mean. Well, we can construct a game tree that relates to the search and that explains the result, so that game tree that you extract in isolation gives a negamax result with the same value as your transposition table search. So it gives you an interpretation of the result.
One last questions while the next speaker is coming to plug their computer.
Is the incorrect algorithm actually correct if you don't have that limit?
So, hi everyone, I'm Rani Ettinger. I've been using Dafny to teach a course on formal languages and automata theory, and I'd like to tell you some of my experiences with this course. So a traditional way of teaching automata theory would be on paper. It's a mathematical effort. It's quite abstract. And when you have bugs in your machines, the designed machines, you will maybe find it when you hand in as a student, your assignment and get the feedback some days later, or maybe even slower. And how do you debug your, even when you realize that there is an error, how do you debug your machine? It could be like a programming effort, right? You could think of this as maybe running your machine, if it would be executable, debugging it, and hopefully also verifying correctness of your machines, of your automata. And this is what I was trying to do with Dafny, and let me share some experiences with that. A little bit about my personal journey with formal methods. It started for my doctoral studies at Oxford, doing program transformations, so refactoring transformations, designing or deriving algorithms with calculational proofs, however, on paper only. And then I've been teaching 3 different courses using Dafny since 2014 in academia. The main one was programming with proofs, and starting with Carol Morgan's book, and then a little bit of Rustan's book. And then that was in an elective course. Then I was asking myself, can I use it in required courses? I did one course on logic and set theory that I presented 2 years ago in London in the Dafny workshop. And then this automata theory and formal languages course. And just to say that this was, I was teaching this 3 times. The last 2 of those in Ramat Gan Academic College in Israel were for students that already studied ahead of that logic and set theory with me in Dafny. So they already knew Dafny, so that made things easier for me on this semester for those 2 times. These days I'm working at NVIDIA doing formal verification for C, combinations of model checking and deductive verification for C, C++, and some Ada and Spark. So my course followed strictly the Elaine Rich, the textbook by Elaine Rich. And in this particular talk, I will show you deterministic finite state machines. However, I've formalized a good portion of the course with Dafny to different levels, so I will show. But let's focus on DFSMs, deterministic finite state machines. So this is from the textbook. So a DFSM, it has states, it has a starting state, it has accepting states, it has a transition function or relation. If it's non-deterministic, this is deterministic, and it has an alphabet. Right? In Dafny, it will look like this. I have here, we have tuples, so I have a quintuple here of sets of states, alphabet, the transition function, and the starting state, and the set of accepting states. For simplicity of this, I had getters with the names from the book, like K, sigma, delta, little s, and a. And then let's make it into a programming course. So let's have, for example, a visualizer. This is something I added after the course, but hopefully for the future. A visualizer, I added that with a kind of a vibe code. It's a visualizer. You can run your machine. You can debug it. Question is, how do you write your machine? So there could be, I could imagine a tool that will help you write the machine. But so far, it's been textually in Dafny, writing the machine. But when I was teaching this course, I gave them a simulator, like in the textbook, DFSM Simulate, that takes a machine and the string, an input string, and prints out those configuration like in a main method. And what's in this simulator, I'd like to show you a little bit how the simulator is written and how is the what's here. This is the machine. So here we have the machine itself. I have a function for the transition function. It would be a relation for a non-deterministic machine. And there is the machine itself, this quintuple. And sorry. So yeah, so what is a formal language? It's an infinite set of strings. What is a string? It's a sequence of characters, or symbols. What is a symbol? It's a character, built-in character from Dafny. So Dafny really helps me. I have some functions about operations on languages. And then here's our language in the textbook, a language for this particular exercise of finding numbers with odd number of ones in them. This is the way with I-set, infinite set comprehension, that it could be written in Dafny. And the textbook had a simulator for the DFSM that was imperative. So I did the same. So here's the DFSM simulate. It takes a machine and a string. It returns a Boolean of whether the string is in the language accepted by that machine. So why is there spaces here? Because I turned it also into to print out the. So it's like a simulator, not only a. So it prints out the states of the machine, but there's more space for the spec saying, well, so accepted should be true if and only if W, the input string, is in the language of the machine. And what does it mean to be in the language of the machine? I formalized it like in the book. And Dafny allowed me to do all that. So that was really nice. Let me quickly go through some definitions to see what do we have here, and ask ourselves, what do the students gain from that, and what does the teacher gain from that? So let's see. For the precondition, we needed to say what is a valid string, that all its characters are from the alphabet, and what is a valid DFSM, that, well, that it doesn't jump, the transitions function does not jump to an unknown state. It should all be correct, and it should be the function should be total in the number, in the states and the alphabet. And then, so this is the language of a machine. It's the all strings that are valid and are accepted by the machine. And this is again from the textbook, just transliterated into Dafny with yielding, what state is yielded by the machine for a certain string. You don't have to read all that now, but and for the post condition, what do we have here? Another function that is the semantics of the machine. It's written in Dafny, and then we are back to the simulator. Now it's a fully verified simulator. Because we know what it means to be the language accepted by a machine, we can add some loop invariants that track the saying really that the suffix that is remaining will end in an accepting state if and only if the original string was from the language of that machine. So that was nice. And that was like a bonus, the verification of this imperative simulator. That what the students gained from this approach is now they can write their own machines and prove correctness. Prove that the machine is really accepting the expected language. A lemma that ensures that the language of the machine they are writing for this example from chapter 5 of the book, example number 4, is the language expected. We have the language, we have the machine, we want to prove. And let's just go through a proof and ask ourselves what's in there. We don't need to understand the proof, but what's in a proof like that? There's a base case for an empty string. There's a non-empty string. There's some calc here that is calling, that is invoking another lemma for each state. There is a lemma for each state, and it kind of tracks the transition function in a way. So it's 5. Thanks. So it's a proof by induction with some calculations, with some well, mutual induction. Like here we see on the calc that we are calling lemma 5,4 for Q naught, for Q0, right, for the first step. And here, in case we see a 1, there is a calling the lemma for itself, so it's recursive, and so on. So the structure of the proof is really, it imitates the structure of the machine. And then students can write their own assignment, homework assignments. They can debug them with the simulator. They can, for bonus points, try to prove correctness. So in summary, for the deterministic finite state machines, what we know now how to do, since we defined formally the semantics of a machine, of the language accepted by a machine, we now have a fully proved interpreter, and the students can write their own proofs of their own machines. So in a way, the theory comes alive. That's the goal of this. So what's more from beyond this in the course? Just a regular second year formal languages and the automata theory course. There's non-deterministic finite state machines, similarly formulated, fully formulated. And then there are parts that are partially formulated, that you have a simulator, but not everything is provable. Like, for example, I love this, the pumping lemma for regular languages. So how can you prove a language is not regular with contradiction, leading to contradiction? There's context-free grammars that will generate all strings possible until a depth of some derivation, some push-down automata, some Turing machines, really beautiful. Only deterministic Turing machines, because otherwise it would be harder. And some of those tools, again, I've been using the textual simulator, and there is also the web one that I generated recently. And potentially then, one could come up with a test suite and either provide it to the students that they will test the work for themselves, or be a teaching assistant in grading eventually. Because if you give it to the students, well, maybe they will do trial and error and not understand really why everything was correct. There are stuff in the course that I didn't do in Dafny at all, decidability questions, parsers, and other algorithms that I did like in the textbook, because that was too much. But if I had more years to teach, that could be great. Finally, the takeaways. It's a way to turn an abstract mathematical course into a concrete programming-like course. It's possible to really fully prove correctness of some things if the definitions are there, and the students are learning by doing. So thanks very much.
For questions while we invited the next speaker to come.
Thank you for the talk. That's amazing. I think I would be very happy, for example, myself, if when I was an undergrad, there was a class with some formalization which helps to run things.
about elections and a project verification of e-voting algorithms in Dafny. So first of all, this is the team, and we're mainly students of computer science in the 5th semester at the University of Regensburg, and we work together with a chair in theoretical computer science, also from the University of Regensburg. And the project took course over the whole last semester, so our 4th semester. And to get into that, I'll first explain what e-voting really is, because that's very important for the project. So what is e-voting? Well, e-voting is basically just holding a normal election, but with the use of computers or voting machines. So instead of people and paper, we try to digitalize it. And this brings some advantages and some disadvantages. For example, advantages are it's very accessible, so for a voter to give a vote via internet is much more easy. And that's great. And also the computing is done very fast. So for complex algorithms, computers are a nice thing to have. Yeah, so that's good, but as always, there are some bad things too. So in this case, with e-voting, a huge issue is trust. So a voter needs to trust the e-voting platform on which he will submit his vote, and that's not that easily given. So there can be problems with the implementation. So is the algorithm really correct? That could be a huge problem. So I want this election to run as it should. And that's one issue, and transparency. So most e-voting platforms at the time don't really show what they're doing behind the scenes. So these were our goals, basically, to build e-voting platforms in which the users could trust. So first thing is we wanted to formally verify our implementations of the voting algorithms, because obviously that is a huge factor for trust if the implementation is formally verified. And second, we made a complete code for the algorithms available for download on our websites and on GitHub to show transparency for the user, so you can check out the code himself. Okay, so the project itself. We started first with researching different voting algorithms, because each voting algorithm has some advantages and disadvantages, but I will come to that later. And then we researched some of them and selected the ones we want to use on our platform. Then we verified them using Dafny, which was the main part of the project, and I will show you some interesting insights on that later. And the third part was that we created 2 websites on which users can hold elections using our verified algorithms. So here is a little screenshot from one election that we did on our platform, and as you can see, it's about the worst Double sequel. We will need that later. Just keep that in mind. So now, the algorithms. So as I said, we used 4 algorithms. So the generalized score voting, the border count, instant runoff voting, and single transferable vote. Some of you may know some of these algorithms. For example, border count is used in the Eurovision Song Contest to elect the winner's song. And a single transferable vote is used in the democratic election of the Senate in Australia. So some algorithms are really important, like this one. And the main difference for us in this whole process was that generalized score voting and border count are algorithms where you basically add up points, and the winner with the most points wins. So they're rather easy to verify, as you all can think of. And instant runoff voting and single transferable vote are round-based algorithms, so they check each round is there a winner, and if not, they eliminate lower candidates and transfer votes and so on. So this makes the whole verification process very interesting and much more harder. Here are some nice little properties of these algorithms. They are important for the algorithms itself and for voting in general or elections, but not for us today, because we want to formally verify them, and we mainly focus on the algorithm itself in that case. So I will explain today. We will look at the instant runoff voting mainly, because I think it's nice to get a little grasp of our process. So first of all, as you can see, it's got a ranked ballot type. And a ranked ballot type is basically just a list on which each voter ranks his preferred candidate from most preferred to least preferred. What's very important is just preferred. If you don't want a candidate to win, don't even rank it. And yeah, so here's again a little screenshot how that interface looks on the website. So you just take your priorities for the candidates. So let's do a little example to explain instant runoff voting, and then I showed you how we verified it. So we have a little election. It's still about the worst Star Wars sequel. So we have 3 candidates, episode 7, 8, and 9. And these are our votes. So we have 12 in total. And now for IRV, so IRV is instant runoff voting. And for a candidate to win, he needs to have the majority of first priority votes. So only our first priority votes counts. This is the first row. And we just add them up. And we can see the result. And no candidate has the majority. So this is bad. Then we eliminate the lowest candidates. In this case, it's episode 7, The Force Awakens. And then we take each ballot on which it was the first priority. So we take at first each ballot and remove that candidate. And then we take each ballot where it was the first priority and transfer it to the next viable candidate. In this case, episode 9. Now, as you can see, The Rise of Skywalker reached the majority and thus is the winner of this election. So that's the basic principle of IRV. Now, our verification process. So here's a little bit of code. I will try to explain most of it with my own words because I think if you didn't work with it, it's not very readable or understandable. So I will really try my best. So the first thing is that our main method for the instant runoff voting takes our candidates. In this case, it's a set of natural numbers. So we encoded each candidate with a natural number to make just the verification process easier. And the votes, so each ranked ballot is a sequence of natural numbers. So it's the ordered list for each voter. And all votes together are just a sequence of natural numbers, so a sequence of these ranked ballots. And we get a natural number back, so it returns this. And this just tells us which candidate won. One important thing is, and the number 0 is not for a candidate. It means that there is no winner, because in this instant runoff voting process, it's possible that we don't have a winner at all. Okay, so this first. And then we have some nice preconditions. In this case, they just make sure that our inputs are valid. So our votes and candidates are valid. And that 0 is not in the candidates, because we need it for the case that there is no winner. Then we have some post-conditions. They are not that interesting as well, except maybe for this, because it makes sure that the winner is really from the candidates, and we just didn't make up any winner. That would be bad. Okay, but these 2 post-conditions are rather important for the round-based verification process. So our approach was we made a ghost function that basically simulates the whole election process, and I will show it later. This is winner ghost function, and what these post conditions mean is basically that if we don't have a winner, that's the first one, then for all candidates, this is winner ghost function will return false. So the candidate really is no winner and shouldn't be a winner. And basically, the next post condition is the same thing, but for a winner. So if we have a candidate that won the election, then this ghost function will return true. So it's basically about this ghost function, which we will look at next. And the ghost function takes in the candidate we want to check, then the candidates and the votes, and returns if that candidate is a winner or not with the given votes and candidates. So what's interesting about this is, so we have this case where a candidate is not a winner. And if that's the case, you shouldn't have the majority, because for this election for the candidate to win in this election, he needs to have the majority. Okay, so this is very important. And the next point is that if a candidate is not a winner, then there is either a winner in this round, or he gets eliminated, that is this, or the candidate won't be a winner in the next round. So we did this by recursively calling this goes function with an updated candidates in lists due to the elimination process. Okay, so the next post condition is basically the same thing for winner. So if a candidate is the winner, then he either has the majority or he will have the majority in the next rounds, which is secured by recursively calling this statement with an updated list of votes and candidates again. So this is basically our approach for the instant runoff voting. For our single transferable vote, that was a little bit more complex. We have a different approach where we save the votes and candidate states from the time the candidate got elected into a list, in which we can argue later on about that timestamp in the election. But I won't show it today because it's too much for this little time slot. Okay, so I hope this was kind of interesting so far for the instant runoff voting. Okay, so let's look at some fun code statistics. We all do love that. Well, we did for all 4 algorithms use 2,385 lines of code in total, of which 1,474 lines are just specifications. That means preconditions, postconditions, assertions, invariants, and so on. So roughly 62% of all of our code are just specifications. And here is a funny little while loop from our single transferable vote method. And as you can see, well, we need some invariants, and the best part is we need all of them. So if we just take one out, it won't the verification process won't terminate or won't really work. Okay, that's very very funny somehow. And then if we take all of our members that just focused on Dafny and divided the hours by the code lines we ended up having in the end, we have about 30 minutes per line of code for these algorithms, which means this process was either very demanding or we're just very slow. So yeah, maybe one of that. And in conclusion, well, we showed with all this project that the verification of round-based voting algorithms is possible, because up to this point we know of no project that even tried to verify round-based voting algorithms, because it's very intuitive to get into. And our next goals would be adding more postconditions. Maybe you saw the criterions I had on the algorithm slide. So there are some very important criterions that we could add for verification in our algorithms. And or we could also add some new algorithms. And yeah, so we have 2 websites. We have an English website that supports the border count and the single transferable vote. We have a German website that supports generalized score voting and instant runoff voting. So if you're interested in them or want to try using them, you can feel free to scan the QR codes and visit our websites and create some elections and send the links to your friends. And what I want to mention as well is the lessons we learned working with Dafny. It's very funny because in the presentation earlier we had very similar lessons learned kinda, because we had the same problem with the statements that we had to outsource into Lemmata, because just the verification process wouldn't even terminate. And we also had some huge methods which we needed to split into sub-methods for our algorithms. And yeah, there's some funny little things about Dafny that you learn while working with it in the process. So yeah, okay. That's all. I hope it was kind of interesting getting this little look into e-voting and verification of those platforms. And yeah, thanks you for the attention.
So I guess thinking about, when people mention that they're concerned about e-voting, I feel like a lot of the concerns wouldn't really be addressed by
of my co-author. So this is the work that we done in collaboration with Mitsubishi Electric Research and Development, a group that appears to be located very near this place. This is about railways and automated trains and in particular the railway networks. So let me explain a bit this context. So in particular in the design of automated trains, there are a representation of the railway network where your trains are running. And so this is more or less a standardized representation of a railway networks using databases. So here is a very simple example. So roughly speaking, the railways are made of segments of rails, and the segments are connected together. So let's see, for example, the segment 2 here in the database has a prev 1, a next 1, and next 2 fields that so seg 1 is the predecessor, and seg 3 and seg 6 are next segments. So this roughly shows you how the connection are described. And you have also switches in the network. So typically the switches will connect 3 segments together. So the tip segment here for switch A, seg 2, and the right and left branches, seg 3 and seg 6. So given this kind of description of a railway network, the question we were asked from Mitsubishi Electric is to check that a given network is satisfying some properties, some structural properties. So the kind of properties that are expected to hold in order for the software in the automated trains to work properly. So this kind of, I'm going to call them invariants, it's a property that should hold for the network, could be very simple like this one. The length of each segment is within some bounds, so segments have some length, but some properties are quite complex, so involving the topology of the network. So here it's not so easy to understand first that it should not be possible to go from the left to the right part of a switch without passing the tip. So let me maybe explain on the picture. The switch C here is not satisfying the property because you can go from the right to the left without passing the tip. Okay, so this is a kind of properties that we should check that in fact are not occurring in the network. So we were asked from our collaborators from Mitsubishi to find a way to checking this invariant, and with maybe 2 main goals in mind. It should be efficient, but it should be come with a high level of guarantee. So that's where we wanted to work on. In my group, we are not very familiar with Dafny, but more with Y3. So we think that it's a perfect application for Y3, but it will be the same, of course, for Dafny. Use this kind of environment to design a checker for this kind of constraint, prove it correct, and also run it efficiently. So this is the. So in fact, in particular, let me give you detail. When you define a code like this in Y3, you can compile, execute it by extracting first to OCaml and compile it regularly. So that's the main idea of the tool that we designed. We want to write a tool that will read the database with this CSV file that you have seen before, and we have to write the constraint in some language, some formal language like this one, expressing the simple properties on the length of the segment here. Okay. So we have this picture for describing this little prototype tool. So the central part is designed within Y3, but we have a front end where we do the concrete parsing of files that is done outside the Y3, but it's written in OCaml, and it's perfectly possible to link the verified code and the unverified code. And we get an answer at the end if the constraint is valid, or in fact we want also to have counterexample when it's not valid. But internally, all this is designed within Y3 and proof correct. There is some part of checking properties of database, but the main part is here, the checker. And I'm not going to talk about it, but there is also a question of optimizing the constraint given by the user. So we have to decide what would be the language. So we started from a classical, let's say, first order language, but it's not classical first order because the quantification, in fact, happens on typically a set of segments. So it's in fact a bounded quantification, and the set here is a finite set. And we have in particular some operation of sets, so union or membership, but also the describing set by comprehension, which is important to have for describing the constraint. So what did we do with that? So we define this language within Y3, so it's very easy because we have the way to define algebraic data types within the language. And naturally, we want to define its semantics. So on paper, you will write some inductive rules to define the semantics. And you can map this into inductive definition within Y3. So it's not very readable. You cannot really read here, but it really corresponds to what you would write on paper. So I pretend that this is quite close to what you wrote on paper. So given this semantics, which is quite long to describe because, so sorry, this is an example of the semantics related more to the database, accessing a field in the database. So there are quite a lot of premises to check if the field name is really in the database and so on. But it's quite mathematical and there is no real difficulty. So after this semantics is written, we want to write a code that will check a formula against a database. So it has this prototype, let's say, taking database, local environment because we have local variables, and an expression, and essentially it will return the value of that expression. So this is the specification. So there is a normal exit. So when we want to prove that if it returns the value, it satisfies the semantics that we formalized before. And there are a bunch of exceptional cases because we have to take into account the fact that some data may be not well written, such as a field that does not exist in the database. So given this, so I don't show the code, of course, but there is a code that has some in fact, I have the number of lines. Thank you. So it's roughly the numbers we have for the predicate is 150. The code itself for the program is 250 lines. Let me mention maybe because we have operation on finite set, we are using set of iterators, which are a kind of higher order construct in Y3 that is very nice to use. There are, so the number of VCs here, 182. And yeah, you have some other code when you load the database, but at the end, if you write all this, you can discharge all the VCs with the SMT solver that we have typically in the portfolio in Y3 in fractions of seconds. There is no difficult proof obligation here. So this is the core of the solver, but there is the question about the topology of the network that requires some more complex things. So I'm going to let Noé to explain a little bit what happened with the reachability.
In addition to what Claude just presented, we have some predefined function in which we'll add some arithmetic function, add multiplication, some set operations such as the membership and union. And we also have a way to check the reachability from one segment to another, avoiding a certain set. To achieve that, what we wanted to do is to take a generic model, any kind of algorithm that do reachability in directed graph, and to implement it in YML, and to prove it that it could work. And what we decided was a depth first search, and we also needed an encoding
for our real network because it's not as simple as one could think. We need the encoding because if we want to reach, if we say we want to reach from seg1, seg7, if we just take it as face value, you could say you could do seg1, seg2, seg7. But we're using some train, so once the train goes one direction, you cannot go backward into seg7. But even with the constraint of going always forward, you will go seg1, seg2, seg3, seg6, seg5, seg4, but when you return it, the problem we have is any kind of algorithm that do reachability cannot visit a node twice. So once the seg3 has been visited, when we go back, we cannot visit seg3 again, so we couldn't reach seg7. Our solution to solve this is to duplicate all the segment into two nodes. One node next and one node prev, if you remember the definition we had in the CSV. And so here, if we say we start from seg1, you can clearly see once you go into seg2, there's no way to go to seg7. And when you go through the loop, seg1, seg2, seg3, seg6, 5, 4, you go into the prev, you go back to seg3 prev and not the next. So for the algorithm, it doesn't know that this is the same segment. So it will be able to go through this one and find that there's a path to go to seg7. The semantic we have, our specification, when we ask our solver, does it exist a path avoiding in our graph from one source to a target and avoiding a set A? This function will ensure that the result we have expect that there's a path where we have the definition of path avoiding for graph, source, target, a path, and an avoid. The definition we have of our path avoiding is an inductive one, where the empty set, the empty path, is a vertex to is a path of a vertex to itself, where we just need to ensure that V is part of our graph and V is not part of the set we want to avoid. And for any non-empty path, how do we do it is, if we want to reach from V0, V2, what we need to ensure what we require is just that V0 is not part of the empty set, that there's a path avoiding from V1 to V2, and that V1 is a successor of V0. And in addition, you'll see here that we added V0 in our avoid set to expulse any kind of cycle in our path. Because, yeah. To be able to prove that, our generic model needed 59 VC. To encode the real network, which was a bit more difficult because we needed to take the data, our database, and translate it into vertex. And for each next and for each prev, we needed to have its own function. So there's a lot of VC, but it's mostly just duplicate that we couldn't avoid. And to be able to call our generic model of exist path avoiding, we need to make sure there was some requirement. We need to make sure the requirements are correct. And to do that, in order to do that, we needed 35 VC. Everything was proven with the four classic provers, but it was a bit more difficult than for the prover than the other module, since some VC needed up to 4 seconds to be proven, which is quite a lot in this kind of things.
Okay, thank you. So to conclude, we were able to build an operational prototype for maybe somewhat a simple language, but it's working, it's proved, and it's efficient. So I didn't show there the benchmark that we did. We had some comparison. So please look at the paper that we linked in the program. So we didn't talk about the type checking errors. So this was one requirement given by Mitsubishi Electric, is that if the user is not able to write a well-formed constraint, there should be a nice feedback. So we have that also, but it's not a proof part of the prototype. And so it's important to have also this reporting a counterexample, but okay, see the paper. And we have, in fact, currently a work about optimizing constraints before executing them. So it's important to modify or compile a little bit the constraint before executing them. And in fact, we have ongoing improvement on that, not yet finished. And and maybe let me tell you that the comparison with the tool Ovado is very good for us. We are in fact more efficient than this other tool. Thank you very much.
I have a quick question about the efficiency. So you're doing a depth first search without any dynamic programming kind of structures that would accelerate the search. It's surprising that you're always better than Ovado because they are not doing this, or?
I don't know if you want to answer. It's maybe a bit technical. No. So it's depth first search where we record the visited node, and I'm pretty sure that it's mostly quasi-linear algorithm. Okay, so regarding efficiency, we are search. Regarding Ovado, it's not so easy to compare because with Ovado you have to write a constant, as far as I understand, in a language that is close to the B formalism, and this kind of thing, which is a recursive thing, is quite complex to write using fixed point construction. So it's not a very good. I mean, for the problem is you're not executing the same thing at all. In fact, so the problem is more that it's more difficult to write reachability predicate with this tool.
Is there a last question?
In fact, we started with, we really wanted to use a directed graph algorithm from the shelf, right? Okay,
yeah,
and if we could, in fact, write an ad hoc algorithm for railway network, but it was not very satisfactory. We would like to reuse.
But if it's more, if it would be more efficient, then maybe.
No, I don't think it would be.
Be more efficient, because if the ad hoc solution will have add a lot more step than just doubling the number of segment doesn't cost that much in reality, because yeah, it won't cost much.
Of course, you use more memory somehow.
Yeah.
But regarding the time consumption, I'm thinking it's the same.
Is there like, I mean, I don't know if maybe it's like informal argument that it's basically the same graph. Like it's maybe obvious, but maybe it's good to have a proof that, I don't know, that when you double, it's basically the properties are the same. Like
so I'm not sure I completely remember here, but we have a specification of what is reachability in the network, and we prove that it's the same as the reachability in the encoded graph. I think we have that, but I'm not sure.
Yes, we have that in the encoding
to justify that this is a correct encoding.
That's the main cost of VC is to specify that the segment we have in our database is exactly the same in our vertex in our normal graph.
And with that, let's thank the speakers. So we'll
services this summer in London. This is joint work with Dafny and Olivier, Dafny, and Sunwell, all at AWS. And I'm a PhD student at the University of Cambridge. So I'll be presenting Atlas, which stands for Automated Toolkit for Large-Scale Verified Code Synthesis. Maybe I should just speak down.
Yeah, speak a little bit down.
I'll speak louder.
Yeah.
So, what is Atlas trying to solve? First of all, as we talked all throughout the day today, verifying in Dafny and in auto-active verifiers is a hard task. And this is seen by the number of data points we can train. Publicly available files. The difference is lost. And because of that difference, we can argue that
Sorry, what the fuck?
that are fit for Python and Java, the AIDA Copilot like code verification are simply not available in auto-active verifiers. The difference of how training data affects like Copilot performance is seen in Lean, where with community adoption tools have become a lot better, and there's no reason for why this is not possible in Dafny and auto-active verifiers in here. And the human labor is really expensive. Writing Dafny proofs, as we've seen today, can be 30 minutes per line of code in even mid-scale projects. And this is really bad if we want to scale this in the next 20 years. So what's our solution? In this line of my internship, we identified a data set of the sort of problems that we could potentially look at and formalize into Dafny using the compiler feedback hints that we can track correctly. So such data set we looked at is Python verified. It contains around 30,000 programming context problems in Python. Those Python solutions to the problems have reference test cases as well as some metadata that will. It covers competitive programming problems from LeetCode, code forces, and HackerRank, as well as other sort of online available building. The limitation of why this is not possible in principle is simply due to the fact that Python is an inverted programming language. It doesn't have the same type restrictions on specification synthesis is simply a very hard task. So a naive translation of Python to Dafny to get more data in Dafny is really difficult. Throughout this informed description of the problem, we came up with our translation pipeline, which leverages compiler feedback in Dafny in multiple stages and allows for the model synthesizing the program to self-correct multiple times. So first of all, when we get a problem into our data set, we synthesize its method signature.
Our ground truth method signature that we will never change throughout the pipeline. From then onwards, we really want to make sure that the specification and the test cases are ground truth examples for that particular pipeline synthesis. And then we move into the implementation and proof stage, where we implement the implementation to the signature. And in Dafny, this happens all in one stage. So we add the necessary assertions as well to track. The reason why we chose this particular sequence is that once you're done with one part of the pipeline, then you can effectively freeze it and move on to the next step without going back, sort of any further back than you need to. An example of such how such a pipeline tracks is the following. If we have a very simple problem, such as implementing a function that checks if a given string is a palindrome, the question will be stated in natural language. We'll have a reference Python solution, which in this case is, notice, very hard to translate into Dafny because of the particular syntax used. And then we'll ask the model to generate only the method signature in Dafny, which is the output here. And then, given the method signature, we'll ask it to generate the specification on one side without generating the implementation at all for now. And then we'll ask it to generate the test cases in parallel. So both of these we can check given the method signature that they compile, with the compiler telling us that it's unimplemented yet, but at least we can check for syntactic correctness in Dafny. And these test cases are also translated naturally from the reference test cases that we see in Taco Verified. So once we have our sort of stage set of like what the program will be aiming to solve, once we have the specification and tests, we can put them together. So in this particular case, the model came up with an extra predicate and an extra function for the palindrome method signature. Then it came up with the specification in the previous stage. We put the method for the test below that in the bottom of the file. And then this is our ground truth. We fix that. We freeze the problem. We do not allow the model to change none of the test cases or none of the requires or ensures clauses. And we only allow the model to implement the method. And this allows us to, again, sort of safely implement as well as use Dafny error feedback to sort of bootstrap our knowledge as we go along. However, one of the limitations in all of this automated synthesis is that Python programs, they do not have specs given in the data set. You have to come up with the specification as you go along. And the two main problems we've noticed with specification quality are too restrictive of a specification. So specifications that essentially make the prerequisites too difficult. This happens less often than the second one, but we'll talk about the first one now. So if the specification is too restrictive, then if we take the specification, so all of the requires clauses for this particular problem and all of the ensures clauses at the bottom for this particular problem, and we require all of the test input assumptions, and we also require all of the output assumptions. So here we're fixing the output here, that is day, to be equal to 3. Then this should verify. We should be able to prove that in this particular instance, we should be able to derive the ensures clauses. In cases where we cannot derive it, it's either that the solver in and of itself is too weak, so Dafny simply cannot one-shot this lemma, and in some cases that's fine. But if in all of our test cases this is true, then it's a flag that our implementation, the specification we came up with, it's too restrictive. Another way that we can tackle this is on the other side, which happens a lot more. Sometimes specifications are simply underspecified. For problems that require optimality, such as finding the maximum contiguous subarray, the maximum sum in a contiguous subarray, you need to really state optimality conditions, and models that are not as good at Dafny really struggle with this right now. So the way to check for this particular instance we found is using two methods. First, we may attempt to prove a contradiction, assuming the output is not the ground truth value. So if you remember the previous example, here we will assume that in this particular instance, output day was equal to 1. We'll assume that day is not equal to 1, and we'll have all of the previous ensures clauses as now preconditions, requires clauses, and we'll aim to prove false. So this should be, in principle, provable. Again, depends on how good the Dafny SMT automation is for how many proofs that this actually comes up with. And in the other case, we may be able to not strictly prove false if the method, if the output is assumed to not be the ground truth example. But if we perturb it, then in the cases where we are still able to derive the post condition, it means that this particular output can range a variety of values, so it's underspecified. So these are the methods that we use to ensure specification quality, and we propagated this feedback from the compiler to the model as it was going through the pipeline to self-correct. So what did we get? Firstly, we instantiated the model with the pipeline with Claude Sonnet 3.7, and for the first stage of the pipeline, getting the specification and test cases, when you have the method, we have over 5,000 compiling files. Given these over 5,000 compiling files, so this is nearly a success rate of 50%, slightly less, then we went in and, freezing the specification and test cases, looked for implementations and proof of those programs. We found that through a fixed budget of error correction, we were able to synthesize 2,751 files solely from scratch, passing the specifications and the test cases and running the test cases without errors. Sort of something I'll come back into the future of this talk, we keep all of the positive and negative inferences for possible reuse later. So not only the 2,700 programs make it to the final data set, but we also keep all of the error correction chains that allowed us to find the final solution. I mentioned Taco Verified has metadata, and this is a snapshot of that metadata. It stores the problems into skill types. Although the success rates in most of them are sort of quite low on this on this graph, it really still varies by type. For example, there's some problems such as sorting and range queries, which typically think about sort of mutable arrays and objects that don't think about a single element, but rather a group of elements, where the models are performing worse. And comparatively, on bit manipulation, for example, the models are performing comparatively better. So we need more data on this to think about where automatic code verification can be better or worse domain-wise, but there can be an early indication of such fact. Right. So I mentioned that I'll come back to the fact that we keep all positive and negative inferences for possible future reuse. We do this exactly in the way we create our fine-tuning data set. So given the data, all of the new Dafny programs we've generated, we needed to validate that this is actually useful for AI model training, because having more data is good, but we need to show that it's useful, that it's more useful than the stuff that the models are trained on beforehand. So to maximize efficiency, we not only look at the first top row of natural language decode synthesis data points, but we also split up all of the percentage is wrong. Sorry. We look at all of the possible other ways to synthesize these programs. In particular, we can look at implementation repair. This particular row corresponds to the fact that once we are implementing the fixed specification and test cases, if we make an error, then we might be able to use might be able to train on the fact that if you made a mistake, the error feedback was precisely this, and we fixed it in a particular way. So, for example, implementation infilling is this part of the pipeline where we ask the model to implement. It makes an error correction attempt and then comes up with a correct example. So to show our efficacy of our method, we evaluated on 2 benchmarks, which I'm sure will be discussed in the further talks in this session. We took a simple model that is known to be a good open source coding model, Qwen 2.5 Coder 7b, evaluated on 2 benchmarks, so Dafny Bench and Dafny Synthesis, one addressing simply proof infilling, so assertions, adding assertions to an existing implementation, and the other generating the Dafny implementations given test cases and a method. And we showed significant improvement from the base model, being quite competitive with prior frontier models during the benchmark release. So showing that this sort of synthetic data that we can generate really works. So to conclude, we have a data set of nearly 3,000 verified programs leveraging intermediate Dafny feedback. Soundness and completeness lemmas really help us get a higher quality of a specification during generation. We split our fine-tuning data set into multiple training examples per pipeline run. And this is a really promising way to train copilots for Dafny, is our conclusion.
I think we have time for one question.
So you were talking about translating the test cases as well, but actually the test cases, I imagine that they're like just comparison of function applications. So I guess you can actually have a faithful translation to Dafny.
Yes.
Like you don't need an.
So we found that in about half of the cases this is true. However, some types still don't match. For example, if you're thinking about a matrix, for example, the way you represent a matrix in Python versus in Dafny varies a lot. So you would still have to have that type translation, and we chose to automate it with LLMs in our model.
Okay, but because the type translation itself, I think you could like systematize that. And I don't.
It's possible, but we didn't want to equate for all of the cases sort of by hand.
Generate formally verified code. So what and then for that, like it was mentioned, like we need somehow to build data that is, we know, like we can use that data to actually train these models to
well, they already generate relatively good verified code, but like to even improve their rate, their success rate, we'll need to like train the models in this view. So, well, this is just like to show that like from the 80s, we've had problems like disasters which are actually due to bugs in software. So problem is that these days more and more software is like, we have even more software, like software is everywhere. So like then definitely we will have more bugs. Like we have bugs that we know of, we have bugs that we don't know of but are exploited. And then, so now at the same time, like we had AI capabilities going, like we get better and better AI at various well-defined problems. But now, actually recently, is that AI is being used for like everything, like just coding, ChatGPT, video agents. So that might create might multiply our problems. So the question is, how can we like control this kind of AI? And so what we observe at the same time, well, the promise of AI in like doing formal stuff like reasoning and mathematical reasoning. So actually, maybe there's a promise there that we can resolve the tension, the problems of AI with AI itself, and like somehow. So we need to find a kind of framework that will put this kind of constraints on the AI. So that's like we call very coding. Is like just AI coding with AI generated proofs. So we put the constraint. This is the specification. Give me the code, but also give me the proof. Right. So. Well, we all know formal verification. This is like very good. We have no bugs within the spec, so I will not spend time. So this is just repeating like the improvements in mathematical theory improving. The problem is that most of the coding done today is still like with vibe coding. So like we want to see like to set the stage or like to make it more usable in practice to actually do verified coding. So for that we'll need, what do we need? Like we need, well, first of all, like we have the formal verification view, but also the very coding view, which is like you have a specification, then you want to generate the program and the proof. In both of these problems, the specification is important. So we'll need to find a way to give correct specifications to the LLM and make humans actually understand, like write the specification, like even not human, like developers, so not only experts, like even for developers, we want to to find what is the way of writing specifications so that it's clear for Rust developers or Dafny or like, and then program proof generation, which is like a separate task. So this is probably more like, it's still like research to do, but this is like a precise task. So that's something that we can already work with, like, because we can evaluate it. Is it correct? Is the output of the LLM correct or not? So since it's a precise task, we can actually now try to say, so the goal of this work that I'm presenting is that we are trying to accumulate this, like a big benchmark of such precise tasks. So like we have like 10,000 files that like Dafny, Verus, and Lean. And then we did experiments to see, like with various models, which are like a few months old. I think those experiments are a bit outdated, like with all the progress, but it's still interesting to see. We had good results. Now, okay, even better, but there are some problems still, like, because some of the problems might be too easy. Like they come from, we had problems with the formalizations, like some of the specs are maybe simple, so we need to maybe improve the specs. But the idea is that we looked like at a few, like all the available and not available formalizations. So like we started with some benchmarks that exist already, like Dafny bench, which was mentioned earlier. We had like some JetBrains organization had another bench in Rust. These are some benches in Lean. And then we formalized also with maybe an approach similar to what was presented in the earlier talk, this kind of apps and human eval programming problems in with LLM-based approach. Then we also formalized some parts, actually everything from the NumPy library, like this is like Python library. So it's like just to test to see, and there's not like it's like some array manipulation algorithm, and it's not trivial. It's interesting to see how LLM will actually, just given the specification, if the LLM can come up with that. proofs. So this is just like a summary of our approach. So actually, for some of the things we had, for example, Dafny bench, we had 443 files in Dafny. This came in the Dafny bench, I think there are 600, but then we split them into individual tasks. It went to 800 because some files are multiple tasks per file. Then we did some cleaning. I'll present a bit about the cleaning because in Dafny bench, the quality of the bench is not great, so you need to, some of the problems are trivial. There's lots of Fibonacci problems repeated like 10 times, so we had to remove that. Part of it manually, part of it we have like some similarity algorithms but we didn't really apply. I mean, we have thought about it, but like, this is still very much work in progress, how to clean up the specs. Like we have like many specs now, but like I think we need to develop the methods how to clean them up. So, yeah, so this is like just a bit about the sources. This stuff maybe I will not spend much time. So the apps, so we formalized from like Python to Dafny with an LLM generator as judge in between. But then there's you're never we don't have like a formal a rigorous argument that the spec is the same. It's all like based on, we did some manual checks on the random samples, but it's like still works in progress to get the better results. VApps, this is a lean set with 4,000 tasks. We didn't bother translating it because actually translation, this actually costs a lot of money to use the LLM. This is like 4,000 tasks, and then we said, okay, since they are actually still like they're relatively weak, some of them are trivial, so it's not, the value is not clear, but lean still struggles. Like we are surprised, like we'll see the results later, that results in lean is not great. So we it's one of the questions of our work is like why lean for code generation and code proofs is not as good as as we would expect, because it's good at math, but maybe not so good at code yet. So, or maybe the way we wrote the experiments, I'll show a bit. Like I think some of our lean, because we have some, like me myself, I haven't worked with lean, but we have people who have worked in the team, and they said, okay, maybe we need to pass more of the lean state or something like that to the LLM to make more like the work with the LLM look more like the human works, like in the interactive way, like to pass all that information, contextual information to the LLM is not obvious yet. How to, what's the framework for that? Then this is like for Rust. We took like some of the Rust bench. They have a model, some model of human eval, but we looked at their human eval modeling. It's still they have some tasks we could see that it's not great. So I think even for Rust, we don't have yet a bench, a formalization of human eval like we have for lean. I maybe present like the one in lean is. Where is the Verina and I think I skipped here. So Verina and Clever, these are very good clean benches, and then we translated them to Verus and Dafny, but it's still for lean. We have this for lean, but we don't have it really gold standard for human eval in other languages yet. So that's part of the maybe future and ongoing work. This is a bit like NumPy. We generated them in lean with this RECGen Hor triple style. Yeah, BigNum is interesting, and this is, I hope to have time. I'll present some of this is a case study of the difficulty of writing the correct spec, because writing even for big, maybe let me go because I'll run out of time. But what is a spec? I've been talking about tasks and LLM. What we give to the LLM? We give a context, which is basically all the formal definitions, and then we give the specifications. This is the function for which I want the code. And then the LLM will give me some implementation and helpers. So this, for Dafny, it looks like this. This is a valid bit string. This is something in addition. I want to just add two numbers, in crypto operations. These are big strings. So the challenge here, so what is the tasks is to give me the addition of two big integers, so the addition should satisfy that when I transform them into real integers, the mathematical integers, I have this translation function which tells me what is the mathematical value of my string. This is just the classic bit string decomposition. And we have this. Now, the problem with this specification is that, okay, the LLM gives us a solution. So we need to find a way to, I have 5 minutes, okay. Like to say, is this solution correct or not? Like, do we accept it? So it will satisfy, so Dafny guarantees to us that it will satisfy this. But the problem is that there is like for this particular task, there is like the shorthand that the well, not even the humans, they might use like a cheating trick here is that they might first map into the integers, the mathematical integers, perform the addition from the mathematical integers, and then map back. So they would not perform the real addition. So it's very difficult to specify like how to specify that in Dafny, or like I don't know if we have like the tools to specify this, like don't do this kind of cheating. Maybe in Lean we have some more control. So yeah, so like this is like our translation, like because we needed to translate between languages, but okay, I will not spend time. This is like a classic, like okay, we did some specification, like the filtering on specifications, like because like some part of it we did it manually, part of it with some similarity filtering and mapping of specs into this kind of vectors. And then in the very coding pipeline is like we have a spec gives to the LLM that gives us some blocks. We need to first validate the blocks and then verify the file like the Dafny or Verus, or give the error back to the LLM. So maybe this was why the problem was with Lean. Like the Lean was giving us the proof, then we were checking that proof, then you get so, and then that's only for 5 rounds, and that's not gonna work well in all cases. Yeah. So these are like the results. So we got best results with Dafny, yay! But yeah, I think this is because yeah. So we have more. Then we have the a bit less well with Verus, but Verus it's causing all these problems related to big num with interaction to bit strings, and like we have executable types, real types, and like in Dafny we don't have this kind of problems. And the Verus, I must say, that's why I was saying with the compiler message, like LLM, because we give the compiler message to the LLM, but even for humans I can understand, but for LLM, so I think in general we need like the compiler messages could be better for Verus, for example. Yeah, so like we have like some speculative reasons why Dafny is better, but yeah, so like for Lean. We did some vibe coding combining, but it just doesn't add. If you add a natural description, it actually makes it worse. And yeah, then we actually, since we have many NLMs, we just take ensemble. We put them results, like some NLMs solve one problem, another solve another problem. So we put them together. Like this is like what we ensemble method here. So there is future work. Like I was saying, that we need to work on task quality, on more benches, more difficult problems, because still we have like relatively simple problems, and then to improve the performance once we have the bench. So now we have some people who are working on actually reinforcement learning and maybe getting better results from Lean. And then yeah, so that's our conclusion is that yeah, it's something that can be done, and we can work on it. Thanks.
Any questions?
Yeah.
You mentioned that it's expensive. How much did it cost in the what's the ballpark?
Yeah, actually, yeah, I'm a bit embarrassed, but yes, at some point we realized, okay, wait, by this point we spent like, I think we spent at least $20,000. So on the, you know, like, because we had like lots, some of the LLMs are more expensive, like if you had Claude and GPT and things. So yeah, so that's why, like, but yeah, so thanks. It's interesting, yeah, because it's quite interesting that actually this costs. So we need a way to also enable, like maybe people who don't have like good funding to actually run this kind of model. So I think we need to find I don't know, a framework that allows less cost for research. Yeah. Okay.
Any more questions?
let's thank the speaker again.
Thanks.
Yeah, hi everyone. I'm Devangshu. I'm a fourth-year PhD student at UIUC, and I will be presenting our work on generating Dafny annotations with LLMs. So this is a joint work with Stefan and Olivia, and this was done during my internship at Amazon last summer. So yeah, although I think most of the audience are well aware what Dafny annotations is, but I'll give you a brief introductions. Like one of the Dafny annotations is like inductive invariants. You can think of those as hints that help like the Dafny verifier to prove partial correctness of the programs. Like given like the program is terminating, it is correct with respect to the input-output specifications. For example, if you look at the this code, this simple code. So if you just directly try to verify this code with the Dafny verifier, it doesn't go through. But in order to get the proof verified with respect to the input-output specification, you need to add this inductive invariance, which essentially helps like the Dafny verifier to prove the correctness of the programs. Now, the question is who actually provides these annotations. Currently, it is done by like the developer themselves, but as you can see, like the providing these annotations can be quite time-consuming, and also it's not that easy. So this is where the LLMs comes into pictures, and we can actually use like the LLM to generate these annotations. So what exactly like the problem we are trying to solve is like given a base program without any annotations, we are trying to generate these annotations that essentially help us prove the LLM to be correct with this input-output specifications. Now there has been already some prior works we try to address these problems, and also there is some benchmarks like Dafny Bench, which essentially targeted for this problem. Now in this talk, I'll be mostly focusing on like some inference type strategies, which essentially helps like improve the LLM performance on this task. And also more importantly, I'll be talking about some common pitfalls, like some soundness bugs we should be very careful about while using LLMs for this annotation generation task. And overall, we'll build on these strategies to come up with an inference type agentic framework, Dafny Pro, which both improves performance and the correctness over the prior works. And as we can see, like we can use this Dafny Pro, this inference type frameworks, and like frontier models to actually curate data sets, which can be subsequently used to improve like the performance of the smaller LLMs by fine tuning. So, but yeah, in this talk, I'll be mostly focusing on like the inference time framework, and I will refer the audience to check the fine tuning results from the paper. Now, what is like the primary strategy that has been utilized in the prior works is to generate multiple attempts through the LLMs with annotated code iteratively and try to verify those annotated code with the Dafny verifier. If the annotated code succeeds, we stop there. Otherwise, you use like the Dafny error message as feedback to guide LLM to generate the next annotated code. So how this works, so this is like the first attempt generated by the LLM, which doesn't actually get proved because like the invariance it predicts is not actually inductive. But if you pass it to the Dafny verifier, this is like the error message. Now if you feed this error message back to the LLM and regenerate again, the LLM now provides a inductive invariance, and that was actually able to prove the correctness of the program with respect to the pre and post condition. Now one key details I have skipped is like how these annotations are generated. The common techniques that are used in the prior works is to regenerate the entire code with these annotations. This is done because it can be like there can be nested loops, and you need to insert assertion statements to guide the Dafny verifier at different program locations. So it's easier to regenerate the entire code with annotations. However, this comes with one concern that sometimes like the frontier models actually cheat and essentially modifies the base code logic to essentially push the proof over the line. And some of the prior works actually have this problem. They had used some basic string-based ad hoc techniques to check whether the base code is getting modified or not, but there are always these corner cases that has been missed. So blindly trusting like the LLM to regenerate the entire annotated code again can be risky. This is why our first contribution is like to formally check whether like the annotated code modifies the base code logic or not. We take both the base code and the annotated code, pass it to Dafny verifier, and check whether the added programming blocks can be exactly parsed as annotations like invariants, ranking functions, or assertion statements. If not, we return the error message, and if only the merge is successful, then we move to the next step, which is calling the Dafny verifier. So with this gives us the first attempt we took. So essentially, given a base code, we generate the annotated code with the LLM and pass it to the code merger. If it fails, we return the error message and retry again. And if the merging successful, only then we move to the Dafny verifier. And if it is verified, we stop there. Otherwise, we retry again with the error message. Now we'll be I'll be reviewing like both the successful attempts and like the failure cases to further improve the pipeline. So if you can see this program, so actually like the frontier LLMs like Claude is actually quite good in finding this invariance. For the example, it could find like the correct inductive invariance that prove the correctness of this selection sort program, which has multiple nested loop. Now where actually things are failing. So for example, if you look at this case, we found out like the LLM generated invariants are actually quite close to proving the property, but it was actually not quite there. So it was actually missing some small bits of information that could push the proof over the line. For example, if we look at with this set of invariants, what we couldn't actually prove like the post condition, but what we could prove that this property, which is quite similar to the post condition, but not quite there. But if we look at like the ground truth of this attempt, like what was missing was this additional assertion statement about the array slicing, which essentially pushes the proof over the line. So this assertion statement, like the LLM couldn't figure out, and if you don't provide this hints, actually like the LLM based search gets derailed and it tries to add some invariance that is not inductive, and essentially over the 10 attempts it couldn't get the proof over the line. And one good thing about this problem is like if you look at like the assertion statement, it was not really specific to the problem itself. It is more like a property of array slicing. So what we can do, we can build a data set of this type of hints, which are problem independent, and use this data set during this generation. So we can call this data set with the context, like the previous attempts and the error messages, and retrieve relevant hint from this data set, and which actually guides the LLM generation in the subsequent attempts. So this is what we call hint augmented generation. So now the question is like how actually we retrieve these hints. So we can actually use an LLM itself, like which essentially, given the context or all the failure attempts and the error messages, it calls like the retrieves relevant hints from the data set. And the second question is how we can like build this set of hints automatically. So for this, we also use LLMs. Like given a wrong attempt and the ground truth problem, we can actually use the LLM to find what was like the missing bits here. So for example, like the example I shown in the previous slide, it actually figures out like what should be the missing link, so that the proofs can go over the line. The next issue we figure out is like the frontier models are quite verbose. That means like it adds way more invariant clauses that is actually required. So one of them is not proved to be inductive, then the entire proof fails. But what we observed, like if we just ignore that specific invariant clause, with the rest of the invariants it can actually prove the property. So the best simple solution is just to prune out those additional invariants and try to prove the output specification with the rest of the invariants. That becomes our second strategy. So what we do in this case, like in the inference time framework, if you get an annotated code which is unverified, so with some invariant clauses that are not proved to be inductive, we greedily prune out those invariant clauses that are not proven to be inductive and try to prove the post condition with the rest of the invariants. So now how we decide which invariants to be pruned? We just greedily decide on pruning all the invariance clauses that are not proved to be inductive. Now with this, we arrive at our inference time agentic frameworks, which builds on like the first attempts with this two additional component, which is like the hint augmentation that retrieves relevant hints for the context, and the invariant prover, which try to detect whether there is some invariance that is unnecessary and which is not proven to be inductive, and prune those out and try with the rest of the invariant clauses. Now we evaluated our Dafny Pro framework on these 4 data sets, in which like the Dafny, which is like the largest data set we have. So for all all of these benchmarks, we evaluated like what is the percentage of programs that are verified by the Dafny Pro framework. And for each of this problem, we gave LLM multiple attempts, which consists of 3 different steps, which is like prediction, which is like the annotated code generation, pruning, like removing some invariants that are not needed, and the hint retrieval step. So this is like the results on like the Dafny. So on different benchmarks with like the Claude 3.5 and Claude 3.7 model. So in blue we showed like the first attempt results, which didn't use like the hint augmentation and the pruning stuff, and we show like we significantly improve on with Dafny Pro with those 2 additional steps. Now these are the numbers. So with Dafny bench, which is like the largest available benchmarks, which actually go near 86% of the problems to be verified by Claude 3.5. Now if we look at the breakdown of the improvement, so if we see like the hint augmented generation results in like the highest jump in the number of percentage of verified programs. And now one important observation is like we found like some of the programs used in the Dafny bench was actually faulty, so we fixed those examples with essentially the rewrite that we use for the deep merging strategy, and that also improved the performance by 3 to 4%. Now I will be actually going over some specific examples where like the hint augmented generation is actually improves performance. So this was like the example which motivated this hint augmented generation. And if you see with Dafny 4, actually the LLMs figures out the correct hint. And not only that, given like the hint is actually not dependent on the very specific problem, it's like more dependent on the array slicing property, is actually generalized for other problems as well. For example, this is another case where explicitly adding the same assertion statements pushes the proof over the line. So yeah, with that, I'll conclude my talk with 4 more representative slides from the presentations. So first, we described about the cheating examples and how to prevent like how to ensure like the soundness of the LLM based annotation generation of the Dafny programs. Second, we discussed about like the hint augmentation strategies and show that it can be very useful technique to improve the performance of the verified program like annotation generation. Like then we discussed like the overthinking problem and like the pruning strategy, and then like the Dafny Pro agentic framework that's essentially combines all the components and yeah, gets very good results on like existing benchmarks like Dafny Bench.
Any questions?
And if the next speaker can come.
So this is more of a remark than a question. So this work was done this year?
Yes.
Or last? Okay. So
it's 2025.
So it must have helped the frontier from
This is yet again work done during my internship this summer at AWS, this time with Stefan and Olivier. And it is on a benchmark translating mini F2F, a math benchmark, into Dafny, and then checking how well does LLM-guided mathematical proof synthesis work in an autoactive verification domain. So since the audience, I assume, is mostly into autoactive verifiers, I'll do a background slide on mini F2F. Mini F2F is a benchmark released by OpenAI in 2021. Originally, it was in Lean 3 and MetaMath, partially in Isabelle and Whole Light. Those translations have then been made full, and then later translated into Coq and Lean 4 when that came out. It is composed of nearly 500 problems, split in equal to test and validation set. It is sourced from the International Math Olympiad, AMC, AIME, and other competitions, as well as undergraduate curricula. The reason why I'm even talking about it is that it still is, and definitely was, the de facto standard mathematical benchmark for neural reasoning in interactive theorem provers since its release to 2025. So just to get a sense of like what this benchmark even is, here's an example problem. In natural language, the problem is the following. You have a set of positive integers, a, b, then their difference, then their sum, assumed to be all prime numbers. And then you're given the multiple choice question of if the sum of these four numbers is one of the following. And this presents a bit of a problem, like how do you formalize this? And at the time in 2021, the sort of way to formalize this, or like the natural way people did it, was they picked the answer and they formalized it as sort of an unfaithful translation without having to guess the answer. So the benchmark is formalized in this way, and this follows for IMO problems and such. As I was mentioning, originally it was in Lean 3. And this is important because if we go and look through the times in history, and I've chosen to count today in times of POPLs. So starting from POPL 2023, this was a benchmark in Lean 3 at the time, and there was some preliminary work on the benchmark with neural models trained primarily at OpenAI, scoring at first just under 30% and then around 40%. And this 40% number, let's keep this in mind, but there was some work being done training models of GPT-3 scale, trying to do neural theorem proving in Lean, and the performance was around 40%. I was definitely not around at POPL 2023, neither I was at POPL 2024, and maybe that's a good thing because the improvement on the benchmark didn't sort of really pick up. There was some work on evaluation of of language models in this domain, but interestingly, throughout this year, there was no real improvement on this benchmark. And then 2025, last year, already a massive amount of models dropped, and performance jumped to around 70%. So this is really the time when these models sort of got a lot more Lean data and started auto-formalizing a lot more Lean data. And the final story of the benchmark is that in the summer of last year, this benchmark was saturated by SeedProver, which is the source from where I took this this figure, reaching 100% performance on the test set, so solving all of the problems. And really, through the range of models that have been developed, this is really a vibrant field. And this benchmark in particular was the leading driver of that. So why the case for MiniF2F in Dafny? The sort of questions we wanted to answer are the following. Firstly, Dafny is known for its sort of easy verification of some of the code you're verifying. So we were just wondering, how does that stack up into a math domain? How can we compare SMT-based automation in Dafny to automation in ITPs such as Sledgehammer and Isabelle, Grind and Lean, and similar? And then secondly, can we leverage neurosymbolic techniques to effectively generate mathematical proofs in an auto-active verifier? So switching domain from ITPs into Dafny here and seeing how effective is this transition. And the contribution we have is the first translation of MiniF2F to an auto-active verifier, accompanied by a proprietary library, as well as a benchmark of a broad range of LLMs testing their abilities to synthesize proofs. While translating this benchmark, some translations were quite obvious and easy. So here's an example Lean 4 statement on the left. We don't need to look at the preamble, but if we look at simply the statement here, all of the lines more or less translate naturally to statements in Dafny. And then the way we state this, we state it as a lemma in Dafny. We have requires and ensures clauses, as is typical, and then we leave the proof as blank for the model to fill in or SMT to solve it automatically. And notice that we include our proprietary definitions and library. That's something I'm going to come back to. But not everything is so easy. Some translations were quite ugly, especially ones that leverage the mathematical library of Lean called MathLib. So there's a good reason for why import MathLib is there at the top of the file. And the reason for that is that once you have something like calling a square root on non-negative reals, or a filter, or a filter dot at top, you're obviously leveraging the library there. And in Dafny, naturally, because of the domain, we had to formalize this ourselves. So we stated it, but we had to make those definitions in our library. And these are the particular sort of predicates that we had to formalize. How do we do it? So in Lean, everything is foundational, and MATLAB is derived from foundations. So the community does not allow for contributions that have partial completeness. However, for us, we didn't aim to redevelop MATLAB from scratch. We don't think this is the notion of autoactive, this is not the standard in autoactive verification, nor for this project. We simply wanted testability, hence we axiomatized the predicates required to state these problems in the definitions file. So each of the predicates has the axiom keyword in Dafny, and this in particular axiomatizes limit definition. Whether this limit definition is actually workable in Dafny is to be seen. I mean, the triggers do trigger, but it potentially is requires a large library for this to be actually useful. So just to recap our approach, we defined all of the necessary concepts to define this benchmark. We introduced a compact library of just over 100 axiomatized lemmas. So neither for the lemmas nor for the predicates, we actually added proofs. But these lemmas are well-known facts, some translations from facts in MATLAB about the concepts required to prove these problems. And then we prioritize capability over completeness. So we wanted to show to test whether it's in principle from these axioms possible to verify these statements instead of being complete here. And the big punchline at first, once the formalization, the translation was done, was that 40% of the test set were solved automatically in Dafny without a proof. Without an LLM-generated proof, that is. This number is actually higher even on the validation set, reaching around 45%. But if you remember in 2024, in Lean, this was the state of the art. Training models of GPT-3 size. So we had, Dafny has something right. In Dafny, automation is powerful enough to handle 40% of these quite complex problems. And a particular success case that we were very sort of inspired by and just in general interested in was IMO 1095 problem 1. This famous problem is known to be as one of the easiest IMO problems because it's one of the first IMOs ever held. And here's a proof from the model that saturated the benchmark, Seed Prover. The formatting was fit to make the slide, but it's roughly 15 lines of code. In Dafny, that's trivial. It's just an empty proof. The proof, as sort of is always is in the pudding. The way we axiomatize GCD has the required requires and ensures clauses to propagate the statement. However, this is really, really impressive. Synthesizing automatically synthesizing a solution for an IMO problem without any particular tuning for the system. However, we have 40% of the proofs. We don't have the remainder. Another thing that we wanted to test was the compatibility of LLMs to automatically synthesize Dafny proofs in a mathematical environment. So we tasked LLMs that we could get access to synthesize proof hints and auxiliary lemmas to complete these proofs. We noticed that some of the proofs might be easier to modularize, so we allowed for auxiliary definitions, but we never allowed for the models to change the specification. So the requires and ensures clauses had to stay exactly the same. And we didn't allow for adding any axioms within the so we didn't allow cheating essentially for the models. We had 12 models benchmarked in total, and here are the results. In our methodology, each attempt here corresponds to the LLM iteratively attempting for 4 attempts. So that is attempting once, then getting error feedback from Dafny up to 4 times in that fashion, and then we ran up to 4 such parallel attempts. So the baseline on the left is around 40%, and we saw that the best model at the time of testing was Sonnet 4.5, reaching around 55.7% performance. So much lower and definitely not saturating the benchmark as in Lean. However, still there were some inferences where the models helped push the automation over the edge. Some models are much worse. So interestingly, Haiku was only 44%. So just essentially a few problems over baseline. And the general gist of the models we tested was that they fell somewhere in the 50% bucket. So not a huge improvement, showing that these models were not really trained for this task in Dafny, however showing some capability. How does this look like? An example problem where the proof doesn't get automatically synthesized is the following induction problem, showing that taking 4 to the power n plus 1 and adding 20 is always 0 modulo 12. So of course on the left I've shown in my editor that this doesn't pass the compiler, but on the right this is a proof generated by Sonnet. So naturally, given it's an induction proof, the model splits it up into a base case of n equals 0, does the required assertions there, and otherwise calls the inductive step and generates the required assertions to prove it. So really, in principle, this is possible. However, due to limitations of the model training, both in Dafny and as well as our proprietary library perhaps being a bit too small, we didn't see performance matching the performance in Lean. Just to recap the limitations, brittleness is still a huge limitation even when LLMs come into play. Minor changes in assertion order or even calc statements do change the cause of verification failures. The models might be changing, fixing one error that it got in a particular error correction run, and then even though the rest of the proof body doesn't change, another brittle error comes up afterwards due to the changes in the assertion order introduced in that way. So better error feedback and what we heard about a more stateful Dafny would definitely help here for the models to get better feedback from the system. Otherwise, we saw some syntax confusion. So models do tend to mix Dafny syntax with Lean and Coq. And I'm interested whether this is because the models were trained on a subset of mini-F2F code, so them thinking that this is mathematical theorem proving I'm doing, so I'm calling some Lean definitions and Lean lemmas. But in general, this is a huge limitation because the models might have the proof 90% correct, but if they call a given Lean lemma, then of course you just you waste your attempt. And of course, our lemmas library might be expanded, and it would be interesting to track how that improves performance. So to recap, main takeaways. Firstly, Dafny's SMT's automation is very powerful compared to existing automation in other interactive theorem provers. Just to give you some numbers, Sledgehammer and Isabelle scores around 10% in mini-F2F, and the best numbers I've seen in Lean, and there's a chance that it was optimized for Lean, score around 27%. So Dafny still outperforms by quite a bit. Secondly, LLMs can be successfully used to synthesize Dafny proofs for complex math problems. And that's sort of a new finding we've seen. And then to leave you, we have two questions. So through our work, finding some IMO problems being solved with no proof at all, or no proof that we can read at all, and some proofs being quite verbose that are LM generated. I think this poses a question: what proofs are best for researchers to interact with? Like, do we even want to see the proof? And I'm going quite aggressive here. And then what proofs are best to train models with? Of course, we want some interactive feedback. So if all of the proofs in Dafny are either empty or super long, that might not be good to train these systems as well. So just leaving you with a few questions. Thank you.
Time for one question.
Thank you. Yeah, that's very interesting. It's a very interesting experiment. I have a question about where did you draw the line, what to put as axioms into these files with definitions? I mean, you could have put the statements themselves, so yeah.
Yeah, so the lemmas I looked quite deeply into and thought that we need to axiomatize it in a way where the definition should be A, usable, and be as close to be fully complete as possible. So for example, for the exponential function, you can think of it as, you define it as 0, you define it to be continuous, and you define its multiplication to be additive. So like, distribute over multiplication. So that sort of ethos was followed throughout the other definitions as well. In principle, from that, everything should be derivable. But of course, MATLAB is much more complete in this.
Right, let's thank the speaker again.
Can you hear us?
Yes, I can hear it. Can you hear me? Okay, so I'll start then.
Okay, can you try to speak again, please?
Sorry?
Okay, can you try to speak again?
Okay,
okay, we are hearing you in the room, so I think you can start.
Okay, so I'm not hearing very well, but I think I can start, so I'll start. Good afternoon, everyone. Thank you for being here. I'll present the paper Specification Guided Repair of Arithmetic Errors in Dafny Programs using LLMs. The authors are Valentina Wu, Alexandre Mendes, and Alexandre Abreu, which is me. We're all part of the University of Porto, and Alexandre Mendes and I are part of the NESTEC lab as well. So it's probably no surprise to anyone there that software bugs are inevitable and they're very expensive to fix. And especially in safety critical systems, in which the assurance of correctness is a very important part of the development process. And in systems verified with formal methods, debugging can be sometimes harder because every fix must preserve the correctness, and also the complexity of the logic reasoning behind the program can sometimes even provide error messages that are difficult to understand. So automated program repair, or APR, aims to reduce this burden by generating patches automatically that will be able to help the developer to fix the problems they're having. So traditional APR tools validate fixes using test suits, but tests are incomplete. So a patch can pass all the tests but still be wrong or still not be the behavior expected. And that also provides the possibility for overfitting. And in contrast, formal specifications express the intended behavior precisely with structures like pre and post conditions. And they can serve as a much stronger oracle for verifying the correctness of the program. And our idea is to bring that strength into the APR process. So our main goal is to automatically repair arithmetic bugs in Dafny programs using their own formal specifications as the ground truth or oracle. And for that, we integrate three components. First of all, we have a file localization component using HOR logic. Then we have pad generation using LLMs, and the verification using Dafny's own verifier process. So we use HOR logic as the theoretical basis for reasoning about correctness. And just very quickly, if anyone is not used to it, a HOR triple like PQR in that format means that P, the precondition P, if that holds before the execution of the command Q, then the postcondition R will hold afterward. So here we have an example where after the increment, the state or the postcondition is the change of the variable I is reflected in the postcondition. And by applying these rules, we can formally derive how each line of code transforms the program's logical state. There has been very few work related with almost the same goal. The main one is AutoFix, but it was made for AFL. And our idea is solving that problem in a different way. We want to use deterministic and non-deterministic components together to help with the APR process. So this is an overview for full pipeline. It's a lot, but we can delve into it. So we start with the Dafny programs, including its own specification. And we first localize the fault using HOR logic and Dafny lemmas. We'll see how that works. Then we generate candidate fixes using one LLM, right, in a specific implementation. And then we insert the answer back into the program for re-verification. The cycle repeats until either a verified patch is found, so a patch that causes the program to be verified, or if all attempts fail. And for each suspicious line, we allow the LLM 3 attempts to fix it. So first of all, and this is an important part of the entire process, we assume that these specifications are correct. So there is a world where the specification is incorrect, and we are not dealing with that. We're dealing with the case where the fault is at the implementation. So first, we encode each of the logical entailments as a Dafny lemma. So the pre-state becomes a requires clause, and the post-state, generally a post-condition, becomes the ensures. And then we ask Dafny verifier to prove it. If it fails, we mark all lines of that block as suspicious, and this gives us a list of potentially false statements without the execution of the code itself. So here we have an example. This is a very simple code, the absolute value of x, and we have an error at the second return, because instead of returning minus x when x is negative, we return x times 1. So we could calculate the states using horror logic, and the states indicate, for example, in case of the if else, inside the if we know the condition is true, in the else we know the condition is not true, so we can update the state using the rules. When we do a return, we also change the return variable if it exists. And for each exit point, we have to check the post conditions. So, for example, the second post condition is tested in the 2 exit points. So in each case, we want to know that this current state implies the post condition. The same thing would happen for the other post condition. And we can check them. In this case, if we checked this one, we would see that it does not hold, revealing that the line, the return line, is suspicious, the second return. So how does that look? In our tool, we first generate a lemma. So we have the current state as requires. So the state was x less than 0 and result is equals to x times 1. And then the ensures is the post condition itself. So in this case, Dafny would not be able to prove it. And once we have the suspicious lines, we can prompt an LLM to repair one of them. So each model receives a structured prompt, as can be seen in the upper image, with the buggy line marked by a comment, and is asked to return only the correct line. And for this example, we can also see an answer on the lower image, and a correct answer, which would be to change return minus x. So some information here is not included for brevity, but the important part is that in the answer of the LLM, you have the patch. So now we can take the patch indicated by the LLM and change the program. And then we can ask the Dafny verifier to say, does this pass the verification now or not? And that concludes the validation part. So the tool is implemented in C#, integrated with the Dafny verifier. It can communicate with local LLMs through LM Studio or call APIs. And when a verified patch is found, we have the entire patch. So we have the location and the content, everything we need to change the program. So we considered many models to be implemented by our tool. And then we ended up choosing these 4 for their open sourceness, their popularity. And in case of Lemma 7b, we wanted to test how a mathematical model would perform in this task, because it includes lots of logic, at least behind the scenes, right? So we evaluated it, and for evaluation we used Dafny Bench, benchmark that was already cited before here in the Dafny 2026. Includes more than 750 verified Dafny programs, including many real world ones. We split the dataset in 2. Ground truth, which is the complete code, and hints removed, which is the code without the invariants and the assertions. We only use code that can be verified for these subsets, because the mutations that will create the bugs will be made by us, which are made with the 4 types of mutations. So we have operator replacement, coefficient modification, variable reordering, and any combination of those 3. And then we also indicate in the source which line was mutated for future reference. So here are the results of the full localization. We had very big success, close to 90%. But in some cases, the coverage for hints removed was around 60%. You can see on the histogram. And for ground truth, it was bigger, close to 80%. So that's the amount of lines that were marked as suspicious. In relation to the repair, GPT-4o Mini outperformed the other models, achieving, if you average both, 74% repair success. And Lemma 7b performed very poorly, likely because it was tuned for mathematical reasoning rather than Dafny syntax or programming in general. So, but that was a test. So we can also see that 90%, 95% changes actually the fault line identified by marked in the source code, and that was and over 80% reproduced the original fix. We can see the data for each one of the models as well in the graphs. And this is also very interesting. The attempts per success, we can see that we get diminishing returns. So if a model does not have a successful result on the first attempt, the second attempt will have even less chance of having one, and the third even less. So you can see it really clearly in the graph. And most for GPT-4o Mini, which had the best success, most of them were fixed already in the first attempt. So there are some limitations we can talk about and some discussion. So while the results are promising, we assume the specifications themselves to be correct, which we talked about before. So if the spec is wrong, so would be the repair. Like we're doing something that we don't want to. We currently only target arithmetic errors, and the performance depends a lot on prompt wording. Finally, and this is important to note, because some LLMs were trained using GitHub data, some Dafny examples from Dafny bench might have been used as a training data for them. So that could slightly inflate the success rate, although the input that we passed to the models were new because we added the mutations to them. So the errors, the faulty programs were new at least. To conclude, our next steps include supporting more bug types. As we said, we only deal with arithmetic ones for now. So control flow ones, for example, would be nice to have. We also want to explore more the repair of the specification itself. So if the specification is the cause of the fault, we want to be able to fix it and not the implementation. This could also be integrated in a VS Code plugin or any IDE, and that would help developers because they can have real-time feedback while they're programming of fixes they could make. And some key takeaways are the big localization success and the repair success, especially of GPT-4o Mini, which was close to 74%. And the integration of Dafny, HoRLogic, and LLMs for repair. Thank you all for your attention. I'll be happy to take questions. And just to finish, I'm part of this lab. If you want to know more about the work, you can access our website or look at the QR code. We have many projects using Dafny, so it's nice. It's interesting if you want. So thank you very much.
Do we have any questions?
Okay, so yeah, I kind of having a side question. So, your implementation, having an assumption that the specification is correct, and then the hard triples used to prove are correct, and you use it to localize your to use for localization. But I have a question that, aside from something like I'm from an Isabelle Hall and Hall 4, and we do a lot of updates, and it breaks, and yes, that is one case then where this kind of thing gonna work. But I want to ask, like, is there a lot of other cases that is might work, because it seems to solve a very specific problem?
Sorry, at the end I got somewhat lost. I don't know it looked like to be breaking. I couldn't hear the end. Sorry.
Yeah. So
like at the end of the questions.
Okay. Is there lots of other cases aside from like Dafny update or something like changing a very small thing in the proof? Is there other cases that this will work?
Maybe, is it possible someone in the support to send the message in text? I cannot, like the microphone is I think you can hear me well, right? Because I haven't received very many, but I only hear everything cut.
After the talk, because now we have to move on with the last talk, sorry. But I hope you can send him the question.
Yeah, you can, sorry. Thank you.
Okay, I'll talk next. And it's interesting that I hear from everyone that we're trying to solve the problem of the equality of the slices of arrays, and we consider it as a very important problem because it's very painful and it's hard to people to debug it. And then we spent a few months to try to solve this problem and really solve it. And then after the release of Cloud 4, and we found it the model, the new frontier model can solve it automatically without any extra help. So then we start to come up with some ideas that whether we can create a benchmark that probably the data set is not in the training data set of the frontier model. So maybe it will beat the frontier models in some way. So I'm going to introduce our paper towards automated contamination-free Dafny benchmark generation. And this is a joint work with Mariano, Dayan, Marco from KTH. And as LLMs are increasingly used for code generation these days, but how to guarantee the correctness of the code is a major challenge. Form verification is one of the strongest way to guarantee, especially for the code generated by LLM, because it can allow automatically feedback for LLM to refine the code is generated until it's reached a valid program. However, form verification is always time-consuming and difficult, which limits its adoption in practice. So we also start to think that whether LLM can help verify the code. And we start with Dafny code verification. So now imagine that we have a Dafny program, which is method, func, and now the program wants to verify it. So it needs to provide a set of contracts. Here we only use a post condition, so we define a func post and put it as a post condition in the method func to try to verify it. And the next step is, of course, try to write some annotations. And here we call it the auxiliary verification code to help the Dafny to reason about the program. This usually takes a lot of efforts by writing invariants, assertions, or even lemmas. So we especially focus on the generation of this auxiliary verification code. So the task becomes that given Dafny program and the Dafny contract, how can LLM generate this auxiliary verification code? So now we have a task. Then how to evaluate LLM the task? We need a benchmark. However, existing Dafny benchmark usually have several limitations. For example, this sometimes doesn't have a clear verification goal. Here, we just need to generate the actual verification code, but sometimes they also need to generate the specifications, a lot of code at the same time. And they don't have a defined structured difficulty level, like easy, medium, or difficulty, and they are vulnerable to contamination because they always use the dataset publicly available, and most of them are manually corrected, so it's hard to scale. And in this work, we want to have a fully automated and contamination-free benchmark for evaluating how well LMN can verify Dafny code. So in this paper, we provide a fully automated benchmark generation pipeline for Dafny verification, also trying to converting some common programming language problem into Dafny verification task. We try to ensure the functional consistency between implementation and the contract by validated through some automatically generated test cases. We propose a contamination-free and a reproducible benchmark design to avoid data leakage. So now, the goal of our benchmarking is to create a set of tasks with, it's not working. Okay. With a set of, the set of tasks consists of a Dafny program and a Dafny contract to be verified. However, how can we get these tasks, and how can we also try to have a clear verification goal and structure the way of structure the definition of difficulty, and also probably can be potentially automated. That's why we also look into the same direction, try to generate this from some common programming context problem like the TACO dataset Marcus had mentioned before. So take this one as example from LeetCode. This is the first task in LeetCode. Given an array of indices, num and an integer target, return the indices that of the two numbers such that they add up to target. So this is a very easy one, but we can see from the platform that they usually provide a solution already. This is usually in some mainstream language, for example, a Python implementation, so we already have a program, but we just need to convert it to Dafny. And it's also described in natural language about what the expected behavior of the program. For example, here, return the indices of two numbers such that they add up to target. So we already have a program and a contract, just in a different format. So the task of TACO Dafny is try to converting them into a Dafny program and Dafny contract. So the first step of TACO Dafny is take the task description to generate and prompt the LM to generate a Dafny program called func without any syntax error, and so that we can try to run it. And in this step, we deliberately ask the LM don't generate any verification code because we only focus on the program, the functional program. So to check this, we also ask another LM to generate a set of test cases, including trying to cover all the edge cases and run it on top of Python implementation to get the output and makeup of our positive test cases pair with input and output so that we can test it on the Dafny code. We can run it. That's a kind of a good point of Dafny because we can run it. So if the output is the same, we can get a correct synthesized Dafny program, at least correct on the LM-generated test cases, and we try to cover as most as possible. Otherwise, we provide a feedback to the LM to refine its code. Then, same for the generation of synthesize of Dafny contract. We extend the same way. We do the task description, ask LM to generate the syntax error-free Dafny contract, func post I and O, and we can evaluate it. We can extend it from the last positive test cases generated in the last step, and we just want to make sure that the contract can evaluate to true on the positive test cases. But this is not enough most of the time, because we can actually define the func post in this way, say it's true, and it still can be evaluated to true on all the positive cases. So that's why we need some negative test cases. And to do so, we ask the LM to generate negative test cases pair with both input and output, and we validate it on the Python implementation as well. So Python actually is a ground truth for us. And we just need to make sure that the output of the Python is different from the output of the test cases, and so that we can get the negative test cases. Otherwise, we'll prompt the LM to generate another new negative test cases. So we have both positive and negative cases, so we can try to evaluate it. So as long as evaluate to true to the test cases positive, evaluate to false to the negative test cases, it's a correct synthesized Dafny contract, at least on the test cases. So we highly depend ourselves on the test cases. It's also our limitation, of course. And otherwise, we provide the feedback as usual. And we now have we now have a contract that is consistent with both the positive cases and negative test cases. But this doesn't guarantee there's a strong it's a strong contract. It's trying to capture all the specifications that we want, all the behaviors that we want. So there's a very preliminary solution here, is that we use model counting. So we ask LM to give us a finite search space definition called finite set, which take input of the input I. So we can count for each fixed input. We can count the output satisfying the contract using this, and we can output how many output that is satisfying this contract within this search space. And if there's exactly one valid output, the specification is extremely strong for us. But of course, this is, as I say, this is a preliminary solution. There's a lot of limitations, for example, because the search space is defined by OM. It could be too large or too small, resulting in timeout or zero solution. And it could be also some cases where model count is greater than 1, and it still have a very good contract. For example, in the two-sum example we mentioned before, if we have nums is sequence of 1 to 3, target is to 3, of course the solution is 1 and 2, because 1 plus 2 is 3. However, the text also saying that we can return the answer in any order, so solution could be both. Solution could be both 1 and 2 and 2 and 1. So model counting is actually greater than 2, but we cannot say the formal contract that gives us this solution is bad. It's also strong. So how to give a smart threshold for this for the model counting, and how to give a smart definition of the search space remains the future work. And beyond specification strengths, we also care about the data contamination. And the key idea here is that tackle Dafny is evaluation first, not data set first. So instead of releasing the fixed benchmark instance, we aim at release only the generation script. So all the user can run the generation script and on all the programming tasks they want. And so instead of making all the data set and example publicly available, so they can also try to choose some programming context problems after the post cutoff date of the model release. So in that case, the task cannot be in the training dataset of the LM. So this helps us to try to remove the contamination and enable a fair and reproducible comparison. And as a preliminary experiment, we have our bench. We applied tackle Dafny to the first 200 lead code problem. The reason why we didn't expand to a few thousand is that we are poor, kind of. Because we don't have $20,000 to spend to generate the benchmark. But yeah, so we after the execution, we used the Cloud for Sonnet to generate the synthesized 76 executable Dafny program with contract to be verified, both of defining Dafny, and both has been validated by the generated test cases. And 51 of them has shown strong specification, which means the model counting is equals to 1. And the one that failing the validation usually means that usually ends up with a timeout because the search space was too long. It's too large. And for evaluation, the goal of a model is actually to generate the auxiliary verification code to help the code to be verified. And we use verified K as an evaluation matrix. K is the maximum amount of interactions with the LM. And a task will be considered solved if the verification can succeed within K iteration rounds. And we set K to 20 in our experiments. We also evaluate our benchmark on several models, some proprietary models and open weight models. And here's the result. The x-axis here is the number of attempts. Y is the verified K. And we can see that Cloud 4 Sonnet is the best one. There's a large gap between other models. And it can solve almost 40% of the tasks in our benchmark within 20 interaction rounds. But GPT-5, GPT-4, even they are also very big, very popular models. They perform much more. And not to mention small models like Llama 3.1, it cannot even solve one single task. And we checked the log of the small models, and we found that they're likely to take a lot of shortcuts by removing some verification tasks or adding a lot of assertions or cheating. And this shows that Dafny verification still remains challenging. And we can also witness that there's a performance improvement as the number of allowed interaction rounds increase. Oh, I also need to mention that by each interaction, we also provide the Dafny error message as a feedback. So that's why it's kind of helping the LLM to refine the verification code based on Dafny error messages, and it's actually helping it because we can see an incrementally increase of the performance. And the final takeaway is that the tasks that are easier to implement tend to be easier to verify as well. And the x-axis here is the difficulty level. And we can see when the difficulty level increases, the verification journey is also dropping dramatically. This is likely to do this is likely due to the complexity of the control flow. A deeper invariance needed, a deeper post condition to be much more complicated post condition to be verified. Okay, to conclude. Tackle Dafny is a fully automated, contamination-free benchmark for Dafny verification. And our results show that Dafny verification is still challenging, even for state-of-the-art LLMs. But our Tackle Dafny try to provide a fair and systematic evaluation. Beyond evaluation, actually, this one has already been explored because the previous speaker has already said that they use the dataset and the traces while synthesizing the code. They can use this dataset and traces to training a new model to make the model become smarter. And it's trying to help to bridge the gap between code generation and formal reasoning. And of course, there are a few open questions. For example, we heavily rely on the verifiability on the test cases generated by LM. It can, in some cases, in the real software development process, there always exists some untested edge cases, and this can potentially make our implementation and the contract not verifiable. So we have some safeguard that because we manually check that most of the tasks are verifiable, and the model have a different performance difference. So this fulfills the goal of having a benchmark to enable a comparable evaluation. Another limitation is that Tackle Dafny now only support the generation of non-ghost specification because we need to execute the specification using the test cases. So how to support Tackle Dafny with non-ghost with a ghost-based specification is also a future problem. But thank you for your listening.
Do we have time for questions?
You mentioned 76 and 51 at the specification and then the model checking stage.
Yep.
What was the number at the implementation generation stage? So you have 76 programs with contracts. I'm just thinking about like the programs without contracts. Like, do you see?
We just we simply remove the one without contracts because like if there's a program without contract, like it doesn't make sense to keep them if there's nothing to be verified.
You take the Python and then you try to translate it into Dafny.
Yep.
Just wondering, like, how much do you end up losing at that stage of the pipeline already?
I think I didn't remember the number, but as I remember, the success rate from Python to Dafny is quite high. So like I would say 150 out of 200, like this.
Thank you.
But the synthesis of the contract is much more difficult, and this is why it makes only 76 in the end.
Are the generated programs with the executable with contracts, are they actually available to read somewhere? Like, see what those generated programs are? Like,
you mean the readability?
Just you have generated some problems that are now verified, and are those problems like available online?
Like, we are not planning to release it because we don't want it to become a training data set in the future model. But I mean, everyone can use a script. We will release a script, and everyone just run a script and training their generating the benchmark by themselves.
Because like part of this is like by LLM, so you provide like a library that will interact with the LLM. Like what is exactly your script doing?
It's a pipeline, the script of the pipeline generating.
The whole pipe.
Yes.
Plug. Okay.
Yep.
Any more questions?
Hi. Did you try evaluating after the model release cutoff date?
Sorry?
So, for example, a model was released at some point of time. Did you evaluate only on problems that were released after that cutoff date? And did you see any drop in performance of those models?
We did it, yes, actually. But the problem is that, so the programming tasks after the cutting off date itself, the verification of it itself is not the same, the verification difficulty of itself is not the same as the one before the cutoff date. So it's like hard to compare because they are not doing the same verification task. But we can try to evaluate, we can try to keep the a potential direction that we can try to, using different models that have different cutting off date and only evaluate on a bunch of fixed data set. But like, for example, a bunch of tasks, and we evaluate the model, there's a model created before this task and after this task, and we can compare the performance of different models. But this also depends on the different, because models have different performance as well. We cannot make them exactly the same.
Okay, thank you.
Okay, so that was the last talk of the day. Thank you everyone for coming. Thanks to all the speakers. Thanks to all the people that reviewed the papers. Thank you to Yannick. This year we've seen by far the most interest in the workshop. I suspect this is because we expanded the scope this year from just Dafny to auto-active verification generally. And I think next year we're probably gonna keep that. So feel free to submit your paper next year as well. And the recording of the workshop is gonna be on YouTube, so you might wanna check that out.
I'd like to add, for those authors who didn't put their paper online, you can still add it to the website. It seems that there's no way to add the slides, but you will have, as Stefan said, the ability to see on YouTube what was recorded. So we had the 18 minutes paper this year, so let's hope for 17 minutes paper next year. Maybe it's equivalent, I don't know, we'll ask Dafny.
Okay. Well, thanks for coming.